Chapter 28 was us learning, getting introduced to magnetic fields. And in terms of practical applications, chapter 28 got us smart about the generalities of magnetic fields. And specifically, they kind of keyed on Hall effect, which is an extremely practical device, motors. And speaking of motors, so let me just go off on a tangent to a tangent. Motors is a gigantic energy sink. So much of our energy today is generated for one reason, and that's to power motors. So I'll come back to this Sankey chart, this Lawrence Livermore energy consumption. This is pretty fresh, 2020. This is a very widely referenced, very widely cited Sankey diagram. And it shows where do we get our raw energy from, and what does it end up, how does it get transformed? And just electricity, if you just look at electricity is over a third. We scoop up all this stuff, we pull stuff out of the ground, or we do a lot of things with fossil fuels and with renewables to generate electricity. And that a lot of that electricity is aimed at running motors. In your car, you go into your car later this afternoon, there's probably 6 or 7 or 8 motors in your car. So anyway, that's chapter 28 at a glance. Chapter mass spectrometers here. That's how, if you've ever wondered, like, how do they separate two substances that are very similar? There's lots of ways, but a very common way is to use a mass spectrometer, because if two particles that have a slightly different mass will bend around in a circular arc after you ionize them and after you subject them to a magnetic field. So if you're playing CSI or Dexter's Lab and you're analyzing something, what do? Well, you ionize it, you strip an electron or you add an electron. So now you have a phosphorus atom that has an electrical charge because you've ionized it. You pass it through a really strong magnetic field and it turns in a circle. And that's that whole centripetal force equaling F equals QV cross B. So chapter 29 is, okay, now that we know what electric fields do to moving charges, this is kind of on the flip side of that. What do moving charges do? And the answer is moving charges create magnetic fields. And again, I'm oversimplifying this, but sort of like the key takeaway, one of the key takeaways from chapter 29 is solenoids. If you understand a solenoid, you understand the magnetic field created by a straight wire, by a single loop, and then by a bunch of loops stacked into a helix or a slinky type of shape. And solenoids are everywhere again because solenoids do work force. And then here we are, chapter 30, induction and inductance generators. So this is where I should have shown, I think. This is where I should have shown my Sankey diagram, because electrical generation, so you have all of this renewable and non-renewable energy aimed at generating electricity. And what is all that electricity? How does that electricity gets generated? How does it get generated? Through electrical generators. What powers electrical generators? And the answer is typically heat. So solar is the one big exception. And you could argue, well, it's maybe hydro too, but solar doesn't need a heat difference to generate electricity, but kind of everything else does. Everything else relies on boiling water or combusting gas. All right, so there. Now we can jump into doing a whole bunch of problems. So I think if you go into, yes, that's good. If you go into Wiley Plus, let's do our first quiz, today's first quiz. And then there's some demonstration videos. There's a ton of demonstrations in the chapter 30 lecture video. This is a very, very basic electrical generator. So what you are looking at an exceptionally basic electrical generator. So if you ever wonder, how does the world create most of its electricity? This is the answer in an extremely simple form. So just because this is simple doesn't mean it's completely unrelated to like the more sophisticated electrical generators. Really, the more sophisticated electrical generators are not that far away from this very, very simple electrical generators. But this is the answer to your question. How do you generate electricity? And the answer is the following. You expose free charges to a changing magnetic field. That's the answer. So again, let me just repeat that. How do I create electricity? And the answer is you expose free charges. Free charges means charges that can move, are free to move. They're not really trapped into their whatever material or whatever space they're occupying. So if you expose free charges, to a changing magnetic field, they will move. The charges will move. And what do you call moving charges? You call it current. And what does current do? It lights a light bulb or powers your electronic device. But that's the answer. And in many ways, this is a large chunk of chapter 30 right here where I'm highlighting in blue, is if you can figure out a way to expose free charges, like the charges that live in a copper wire. Copper wire, again, is a good material because copper is relatively cheap, number one. Number two, it has good structural properties, good thermal properties. Number three, it allows charges to move relatively unimpeded, as do most metals. All right, so now what you have here, in light of that, I actually have a single loop. So I'm just looking at one and only one loop of copper wire. And you're thinking, well, Chris, if one loop generates electricity, why not expose like 10,000 loops? And the answer is, you're right. and generators do have a lot of loops of wire, but we're going to keep things simple. If I expose one single loop of copper wire, and it is important to specify that this is copper wire, copper or silver. The problem with silver is it oxidizes. The problem with gold is better than copper, but it's pretty expensive. Aluminum's a good candidate too. Aluminum's a pretty good candidate and some other things, but copper I think is the most popular. So here is a bunch of free charges. So copper is basically our term for a whole bunch of free charges. And when you expose these free charges to a changing magnetic field, they will move and, again, light a light bulb. So now here's one issue. You're looking at a whole bunch of these magnetic fields right here, X's. X's mean into the page. So this is showing, these X's are showing that the magnetic field is going into the page or into the page. That's what the X's mean. They're flowing away from your eyeball. So be clear on that. And I think a couple of people asked me about that on the exam, which was a little bit surprising, but it's okay, especially since the exam 3 averages were very high. I almost didn't need to do any discounting. But more on that later. So the magnetic field is going into the page, and then you're thinking, wait a minute, that's not the criteria, because I have a copper wire, which is a source of free electrons exposed to a magnetic field, but the magnetic field is not changing. B field is not. So I'm double underlining the word not. I'm highlighting it in blue just for extreme attention. The magnetic field is not changing. So if the magnetic field is not changing, even though it might be a strong magnetic field, no change means no induced current, no voltage. So now, but wait, I'll spin. I will spin the loop, the wire loop. If I spin the wire loop, even though the magnetic field is constant in space and time, if I'm spinning that loop, nature doesn't care. Nature doesn't care if it's the loop that's moving or the magnetic field that's moving. All that has to happen is you have to have these charges in the copper wire exposed to a changing magnetic field. So that works. And this is a very common way to generate electricity. Okay, so that's good to know, because when you expose all of these free charges to a changing magnetic field, you get a voltage. And in this case, they're actually giving you the voltage. They're saying, hey, if you have this situation going on, you have a voltage. Remember, script E stands for EMF, electromotive force, which means the actual source of a voltage. It doesn't refer to just a voltage difference or a voltage drop across a resistor or across a capacitor. It's actually talking about something that makes electricity, which is a generator. So they're saying, hey, you know what? We need to make this generator, which is a loop of wire turning in a circle, that satisfies the following criteria. 2 pi, that is satisfied by the following function. 2 pi f n a b magnetic field. It looks monstrously complicated, but it's really not. So this is the description for the voltage generated by this generator. And I guess one question you could ask is, what's the sine term? Why is there a sine term in this function? Why is it a sine function? And the answer is because this thing's spinning like a circle. If this copper loop is spinning like a circle, what describes a circle? So, and the answer is a sine function. Let me say that again. Uniform circular motion is described by a sinusoidal function, meaning a sine term or a cosine term. Sine terms and cosine terms are basically the mathematical way to talk about uniform circular motion. So even if you're on a Ferris wheel, even if you go to Cedar Point and you sit on a Ferris wheel, here's a Ferris wheel, and this Ferris wheel just turns around in a circle, just spins at a circle at a constant speed, that's uniform circular motion. And the motion can be described using simple harmonic motion, which is a sinusoidal, which is sine-based. Simple harmonic motion or sinusoidal. Sines, cosines. So just a little recap of why this sine function is there. The sine function is there because this is turning around like a circle. Okay, and then, but wait, there's more. Again, the bark is way worse than its bite, but we know from past experience. I mean, we see things like sine of theta. So we see sine of theta, and then we do kind of remember that the definition of angular speed is basically amount of angle per time. Just like going way back, the definition of velocity is distance divided by time. So if the definition of angular speed, that's not W, that's omega. If omega is defined as theta over t, then we can say theta equals omega t. But wait, there's more, because you might also remember, hopefully, that another way to express omega can be expressed as 2 pi f times t. So that's all that's going on here. This argument of sine, which you see right here, 2 pi f t. This is just an alternative to saying sine theta. All of this is the same as theta. And I just wanted to go through step 2 just for nostalgia, just to refresh some stuff. Okay. So, and that's kind of, I guess, what I did over here. They're saying, okay, you have a generator and it's spinning around in a circle. And then here's the big question. What makes this spin in a circle? And the answer is, it could be me. You could hire me to just grab hold of a hand crank and spin that around in a circle. But most commonly, it's jets of steam or combusted gas blowing against turbines that are turning around and around at a very high rate. So we have this generator behaving sinusoidally, which is not a surprise because it's spinning in a circle. And they're saying, okay, you need to design this generator so that this value of NAB, I'm sorry, let me back up. You need to specify NAB so that you produce a voltage of 177 volts. So let's just say for whatever reason, your job is to design a generator that cranks out 177 volts at the rate of 46.7 revolutions per second, and you're exposing this copper wire to a magnetic field of 0.432 Tesla. So this is our dollar sign. Our dollar sign is NAB. And just some words about NAB, about what it all stands for. It's pretty much provided to you. But the N is talking about number of turns. Number of turns. And again, you're thinking, well, if one turn generates some electricity, 10,000 turns would generate a lot more. And the answer is yes, you're right. But there's obviously trade-offs. And A is this, here's A. A is the length and B is the width. So the combination of A times B equals loop area. Okay. So you need to fit, and you have some choices. Maybe you want a huge loop area and only one turn, or maybe you want a small loop area and a whole bunch of turns. But no matter how you design it, no matter how you design this generator, you need to design it so that the product of number of turns times the area of that loop cranks out 177 volts. Oh, and by the way, this is a constraint. You can only cough up a magnetic field that has that strength, and you're limited to 46.7 revolutions per second. All right, so, and then we're kind of almost done. I'm just trying to squeeze out all of this background stuff for perspective because, okay, I need to have E naught, and let me just, some more background. This is technically known as voltage amplitude because the voltage, the voltage is actually, this is alternating current. The voltage is varying between 177 volts to negative 177 volts. It's a sinusoidal. So there's a term. So this is what a sinusoidal looks like this. Let me fix that. This is a sinusoidal. That's a graph. This is a sine wave like this. Okay, so we have this generator. This generator is producing alternating current, which means that sometimes it's positive. It swings from forward and backward. It never really goes anywhere. It just goes forward for a while and then backward for a while. So it never makes any net progress. It just sloshes back and forth, 60 times a second, or in this case, 46.7 times a second. But again, this goes back to simple harmonic motion. You call this amplitude right here, this peak, this is referred to in this case as voltage amplitude. So voltage amplitude is 177 volts. And again, even though I said that, I understand that it's not constantly 177 volts. It just is at the peak and the valley. So at the very tippity top, it's 177, and at the very bottom, it's 177. So that's what E naught is referring to. And they're saying this needs to equal 177 volts. So 177 volts must equal this expression right here. This is what I was doing when I was biding my time. This E naught right here is the same as this combination of stuff here, which is what I wrote down here as well. I basically said, okay, all of this is just basically when let me say it like this. When I multiply all of this good stuff together, all of this is a constant. There's none of this that I'm highlighting is a variable or varies as a function of time. This varies as a function of time. So here's my varying sinusoidal function that's being multiplied by this amplitude right here. Okay, so Apparently, all of that string needs to equal 177 volts must equal 2 times pi times F times NAB, NAB. Little a times little b, again, is the loop area. Big N is the number of turns, times B, the strength of the magnetic field. And then that's why we're done, because you're just going to solve for NAB. So you're going to get the right answer for NAB. It's going to equal 177 volts all over 2 pi F. F, they gave you F. Remember, F is a frequency. It's something per something. In terms of this F right here, this F is frequency. And we know from prior experience, frequency is given in terms of hertz. And we know that a hertz is 1 cycle per second, or 1 revolution per second. So you could actually say 1 cycle per second or 1 revolution per second. And that's saying the same thing. You could actually say one orbit per second. All of those are equivalent. So we know what F is. For me, F is 46.7, and I'm going to write it like this: 46.7 revolutions per second. So here's how I'm going to write this: 46.7 times 1 over seconds. And then B is 0.432 Tesla. And that's the answer. I don't care what N is. I don't care what A is. I don't care what B is. I just care about coughing up a loop of some number of turns and area that gives me 177 volts. Okay. And then as you're getting the right answer, can't help but do dimensional analysis. What is a volt over reciprocal second times Tesla? Well, I know a volt is a joule per coulomb, because volts is delta U over, so I'm just reminding myself, volt is a joule per coulomb, 1 over second, and a Tesla, F equals QVB sine theta. So I'm just remembering B in terms of units. B is newtons per coulomb meters seconds. All right, so then that's a Tesla, Newton seconds per coulomb meter. Okay, so from this, and I'll leave it to you. At this point, you should be able to get, and I can kind of see it right now, you should be able to get meter squared. And I'll leave the rest for you. So I'm making a big deal about dimensional analysis. And again, you need to do it. No dimensional analysis means point deduction. So plus it's a sanity check. All right. That's all I have to say as far as the introduction is concerned. Let's see how people are doing. Okay. All right, then. Before we move on to quiz 2, check this out. You've seen this before, I think.
Finally.
Let me mute this. Let me optimize. All right, so here's arguably the world's simplest electric motor. And you would rightly ask, why am I talking about motors when I just got done saying chapter 30 was generators? But there's a reason. Just check, and we can make this. I have these lying around in my drawer. They're everywhere, these little, and you can make these. You can make these in 3 minutes. But look at this is the world's simplest electric motor. If you take a bunch of copper wire and you expose it to a magnetic field, the charges in that wire feel a force and you get a torque. So this definitely goes back to chapter 28. You are creating a torque on that copper wire loop and you get it spinning. And this spinning copper wire loop is, again, this is a major consumer of fossil fuels and renewable fuels because that costs electricity. You actually have to spend a lot of electricity to make that happen. So I just wanted to throw that out because a motor is literally a generator in reverse. In fact, if I just go back, this is going to look very familiar to a generator because if I take out this battery, so here's what we can do to be clever. Let's take out the battery and let's just spin. Take your hand and just smack that coil. And if you can get that coil to spin, you will actually create energy. You could use this exact same setup, get rid of the battery, and just flick or, again, smack the copper loop with your hand or your fingers, spin it, and then you're going to create electricity. So that's why a motor is a generator in reverse and vice versa. So I wanted just to throw that out there. Okay. And we'll watch another one later. But let me go back into Wiley Plus, and now let's talk about the next quiz. And this will be chapter 30, quiz 2. Chapter 30, quiz 2. It is now 1:37. Okay. All right, you'll see it. Chapter 30, quiz 2. Go ahead and read through that. I'll start jumping in. I'm just going to write this down again. In fact, maybe I'll copy and paste it. I'm just going to go back here because I probably should say this literally 24 times. This statement right here. So again, if you expose free charges to a changing magnetic field, you will generate electricity. So that, again, that's the goal. And you can be enormously creative on how to do that. I mean, Tesla came out with something, I think a year ago, called the reluctance motor, which is like fantastically clever. I mean, we're talking, and there's reluctance generators as well. So there's all kinds of ways to take basic devices and just innovate into, the stratosphere in terms of making something more efficient or more economical or higher performance characteristics. But anyway, this is what's going on here. I have my repository of free charges. So once again, I have a square wire loop. And as soon as you see that word wire means metal. You can say it. So this is my copper wire. I'm just going to say it's a copper wire. Copper is a good source of movable charges, in this case, would be negative charges because the positive charges are sort of locked into the lattice structure of the material. But I'm taking this copper wire and I'm exposing it to a magnetic field. Now, one thing about this magnetic field is constant in space. So it's constant in space. And how do I know it's constant in space? Because you can see that the spacing is uniform. So the spacing between these green dots is the same everywhere. So that's how I can safely say that this magnetic field is constant in space. I can say another thing about the magnetic field. It's coming out of the screen. It's coming towards your eyeball. That's what those dots means. Dots means shooting towards your eyeball like an arrow out of screen. So I'll just say plus K hat direction towards your eyeball. And then there's one other thing I have to be able to say about this magnetic field. It's changing as a function of time, changing in time. So it's constant in space, but it's changing in time. And this is one of the big things about chapter 30. You actually have to worry about space-time, which is a relativity term, but you do have to worry about what's going on in space and what's going on as a function of time. So even more specifically, this is, you're going to deal with spatially varying properties. Physicist saying the screen is not clear for anyone else. It's super blurry for me. So speak up if the screen is super blurry for you, because if it is, the problem is on my side. But spatially varying properties. So we have to worry about spatially varying properties, and there's a number of properties that you have to worry about. And then you also have to worry about temporally. Temporal. Temporally, that's better. All right, so space and time, and it definitely is, I think it's helpful for me to write this down a bunch of times. Spatially varying properties and temporally, which means as a function of time, varying properties. So space-time, things vary as a function of space and as a function of time. And in this case, everything's just sort of sitting there except for one thing. The magnetic field itself is changing as a function of time. So if I went into Desmos and if I just graph this, which I did ahead of time, it's like a cooking show. There's how my magnetic field is changing as a function of time. So if I just take a little snip of this and put it into my notebook, I'll just keep this right here. This is a graph of how my magnetic field is changing as a function of time. And you can see one thing is that as time increases, I'm going to say it like this, as time increases, the magnetic field strength decreases. So this is a major aha, because there's an aha that says, okay, well, I do have a changing field. So delta B does not equal 0. And that means, therefore, if delta B is not equal 0, meaning if delta B is not a constant, if the magnetic field is changing, I get a voltage. I get a voltage. Okay. And there's one other sort of big takeaway just from looking at that graph and looking at this function. Well, I kind of already said it as you could say delta B is less than 0, but I think I have that here. So two takeaways here that I want to stress is the magnetic field is not changing. It is not constant. It is decreasing as a function of time per this function right here. It's a pretty simple function. But that's all I need to know to say, well, apparently there will be an electrical current flowing through this wire because there's going to be a created voltage. All right, so here for the first time is Faraday's law. Number 1, E equals minus N d phi dt. This is Faraday's law. This is the majority of chapter 30 is right here. This is the clear cornerstone of chapter 30 is Faraday's law, named after Michael Faraday, who figured out a bunch of stuff about transformers and motors and generators and etc. We know what a lot of these terms mean. We know that script E stands for EMF. So this is generated voltage. This is generated voltage. So Faraday's law actually makes us a lot smarter about specifically how voltage is generated. This is generated voltage. This, this is number of turns. So we've seen script E before, we've seen N before, we've seen phi before. Phi is flux. And you should be pretty darn familiar with electric flux and magnetic flux. Flux, that term again. And apparently we're taking the time derivative of that. This, last but not least, this negative sign basically is the Lenz's law. Refers to something called Lenz's law. And Lenz's law, you can think of Lenz's law as the price you pay. Because you're basically going to make a deal with nature. You're going to say, hey, nature, if I can figure out a way to create a changing magnetic field and expose free charges to that magnetic field, will you create a voltage for me? Because I want a voltage, because I want to, if I have a voltage, I can make charges flow. Nature says, yes, I will. I will create a voltage under those circumstances, but you're going to have to pay a fee. And the fee is Lenz's law. And we'll get into that right now. All right, so let's solve this. And so that's step one. Start with Faraday's law. Step two, I'm going to do it like this. Okay, Faraday's law, script E, and now I'm going to ignore the negative sign. Ignore negative sign, because the negative sign is basically just telling me that's the price I pay. You guys remember Hooke's law. This is Hooke's law. F equals minus kx, where this is the spring force and this is the spring constant and this is the amount of displacement. You should have definitely dealt with F equals minus kx relatively recently, I would think. And in this case, this negative sign is just referring to the restorative nature of Hooke's law. It means if I stretch a spring, the spring wants to compress. If I compress a spring, the spring wants to stretch, to elongate. So this is referring to a restorative force. And in many ways, you could actually think of Lenz's law as a restorative force. And let me fix my language here. The price that's not right. So I should have said the price you pay, and it's probably actually pretty good. It's the restorative. It's a restorative tendency. That's actually better. A restorative tendency. Restorative means I want to go back home. Restorative means I want to go back to normal, back to home, back to equilibrium. A restorative tendency. All right, so these are good sort of informal ways of talking about the minus sign, Lenz's law. So I'm going to ignore that because, yeah, I get that there's going to be a restorative tendency, and we'll talk about that. What else can I say? N equals 1 right here. So I'm going to I'll add that little note right here. Ignore the negative. N equals number of loops. And you can see right here, I have one loop. I have one square or a rectangular loop. One loop. So this is my updated Faraday's law. I'm gonna start at number 1 again, and then I'm just gonna say, well, okay, this is my situation. I need to figure out how my flux is changing as a function of time. So I'm gonna keep developing this, I need to take the time derivative of my flux. And here's flux. Flux is B dot dA. So this, let me put some parentheses around. No, I guess that's good. This is flux. You've dealt with electric flux before. This is magnetic flux. Very similar in many ways. This is collectively flux, magnetic flux. So magnetic flux is basically a measure of the magnetic fields per area. Amount of magnetic field per area. So amount of magnetic field you could refer to increase number. That's probably saying it sufficient for now. But magnetic flux is amount of magnetic field per area. Just like electric flux was the amount of electric field per area. So this is a cornerstone type of concept, flux. And in keeping with what I've been saying, it's not enough to have flux, because I have flux right here. Here's flux. I can't just be happy with having flux. I actually have to have time-changing flux. And that's what this derivative is doing for me. It's saying, okay, figure out what your flux is and then figure out how it's changing as a function of time. So step number three, the amount of voltage that gets induced due to this changing magnetic field. This changing magnetic field will induce a voltage. All I need to do is, I guess, switch into calculus mode. Integral, and I'm going to go from dot product to magnitude angle. And this is dot product, so it's cosine theta. And you guys have seen this a ton of times by now, where this is the magnitude angle version of dot product. This theta is referring to the angle between the dA vector and the B vector. So we should talk about that. The B vector is right here. B, as mentioned, did I say that? Well, you can see my B vector is in the plus K hat. Is plus K. So the magnetic fields are out of the page. So B is out of page. B is out of page because they're little green dots, not X's, coming towards your eyeball in the plus K direction. And then what's the dA vector? dA refers to differential surface area, differential area. dA vector has a direction. The direction is perpendicular to area. So it's a surface normal. So in this case, I have the magnetic field coming out of the screen towards your eyeball. And if I just look at this area right here, so if I'm just looking, and I'm only going to look at the top half. You know why I'm not going to look at the bottom half? Because the bottom half is not exposed to a magnetic field. So that's kind of not interesting to me. So I'm only going to crosshatch this top half. This is the surface area that's exposed to a changing magnetic field, changing in terms of time, not space. This is my area. And in this case here, this surface area normal, dA normal, well, I'll leave it like that, is also in the plus K direction. So if I try to draw this in 3D, it probably won't go well. But if I just try to do a surface normal, I would draw it something like this. No, not like that, like this maybe. So I would try to show this as best I could as this red vector represents the surface normal vector, which means it's perpendicular to the surface area. And again, this would be my surface normal vector, which would be plus K. So that's all of that deep dive is making sure you're clear on why theta equals 0. Theta equals 0 because the surface normal and the magnetic field are both coming out of the page. Okay. So now what does step 4 look like? All right, 3, 4. So now the induced voltage, what's inducing the voltage? The answer is a changing magnetic field. The induced voltage is d by dt. Let's see here. My magnetic field is not intertwined with the area. So my magnetic field is constant in terms of space because this area traps the spatial component. So flux is talking about strength and an area. You can see, obviously. So my magnetic field does not depend on space, but it does depend on time. So this is why I'm going to write step 4 the way I'm writing. D by dt, and then I'm left with the integral of dA. And I'll just write this down. Cosine of theta, I said theta is equal to 0 degrees. All right, so number 5, we're getting there. What's the induced EMF? What is the EMF induced by this changing magnetic field? I'm going to do dB dt. Cosine of 0 degrees is 1. Integral of dA is just a, and that's our answer. So all we need to do is the following. A, let's see, for me, this is half a square, and I have 1.8 meters. So the area, 1.8 meters per side. Square it, divided by 2. So this is the surface area of my loop that is exposed to a changing magnetic field. And then I take the time derivative of my magnetic field function, which is changing as a function of time, according to this function for me, 0.86 t. And they're saying, okay, so you're going to be creating a voltage, and this voltage is going to be fluctuating, but specifically, I guess that's all we need to worry. I guess that's it. Specifically, what is the voltage under these circumstances? So I guess we can be done in the dimensional analysis. So, okay, let's get an answer on this and then talk about part B. And then do dimensional analysis, 1.8. Oh, yeah, we're not ready for part B yet. Okay. Fizza is saying that she is seeing a blurry screen. I think it's your bandwidth, Fizza, unless again, you guys speak up. If you're seeing a blurry screen, please let me know, because maybe I just need to reboot my Wi-Fi router. So again, please let me know if my screen appears blurry to you. Fizza and anyone else, if you're seeing a blurry screen, then maybe you can do the same thing if you can. Maybe restart your PC, restart your Wi-Fi, your router, do something, because if it's not a bandwidth issue on my end, which would give a blurry screen, it's a bandwidth issue on your end, and just my things to do would be, again, restart my computer, restart my Wi-Fi, and see if that works. But again, everyone and anyone else, let me know if you are also seeing a blurry screen, because the problem could certainly be on my end. All right, but again, we're not actually all that close to being done with this. So this is a good problem, because there's a lot in here, as you can see already. I get this value. I get, this is my induced voltage. My calculator said 1.3932. And then, all right, negative 1.3932 volts. And again, this just cries out for dimensional analysis. And I can see I'm inconsistent with my pens, but then I'm going to say this, ignore negative. Ignore this negative sign. Ignore the negative sign. Use Lenz's law to figure out direction. Use Lenz's law to find direction. Okay. So if I'm going to ignore that, I'm just going to run with this for now. E equals 1.3932. This is the induced voltage. Now we have to talk about Lenz's law. Okay. So, and this will take a long time.
Wait, I'm sorry. How do you get the time value?
When you take the derivative of that function, if I take the derivative of this function, this equals negative 0.86.
Oh.
So time is not a factor here. Okay. So now here comes probably the heaviest part of this problem, and that's Lenz's law. So we're hopefully we're solid in knowing that there is a voltage that just got created. This is the bargain you struck with nature. Nature says, if you can figure out a way to expose a free charge to a changing magnetic field, I will create a voltage for you. And then you will say, thank you very much. And nature says, but I'm going to be restorative. I'm going to ask for payback. So if you look at this magnetic field is decreasing as time goes on. So you know how I'm going to write that? Maybe I better go down here, number 8. All right, as t goes by, so as time goes by, I'll say this, dots diminish, dots get smaller, dots get smaller. Meaning this, as time goes by, the dots get smaller, meaning the magnetic field decreases. And that's why I put up this chart here. This is showing the graph. This is showing the graph of magnetic field versus time. So as the dots get smaller as time ticks by, the magnetic field gets weaker. Gets weaker as time goes by. All right, so you know what? So then, the induced current, there will be an induced current, there will be an induced current that fights this, that tries to counteract it, that tries to counteract this change. What is the change? The change is, well, what's changing the magnetic field? How is the magnetic field changing? It's getting smaller as time ticks by. So we're actually transitioning from big dots at first. So at time equals 0, we have big dots. And then as time ticks by, we have smaller dots. And then as time keeps going, we actually have X's. So we go from big dots to smaller dots to X's. The voltage that gets created will create an induced current that tries to counteract this changing B, this delta B. We know how delta B is changing. It's getting smaller. So you know what? This has to be the direction of the induced current. And then again, just to make sure, why is there current flowing? Why does current magically start flowing through this copper wire? And the answer is because there's a voltage that magically gets created because of the changing magnetic field. So this is going to be the direction of the induced current. I'll write it like this. Ready, set, go. This is the direction of the induced current. So this is I stands for current. IND stands for induced. This is the induced current. Induced means to cajole, to nudge. So this is the induced current to influence And how did I get that? Right-hand rule, PopCan right-hand rule. So a special thanks to PopCan right-hand rule. Because if I do PopCan right-hand rule, which I guess I will now. Okay, so here's my wire. I grab hold of this wire with my official PopCan right-hand rule shape that's frozen in place. If I grab this wire, and if my thumb is going in the indicated direction, my fingers are going to be doing this. My fingers are literally going to be wrapping around this wire and showing the direction of the magnetic field. So this is literally what's going on with my fingers, wrapped around and then coming out this side, producing a dot. Right here, again, my fingers are wrapped around, going underneath, then coming back out and piercing the surface. So I get another dot. Same thing over here. The induced current is it's a single loop. It's a very simple circuit. So my induced current is going in this direction over here. This is also the induced current. And I'm going to do my PopCan right-hand rule. So here's this left top, the left top segment of the wire is what I'm representing here with this pen. I grab hold using PopCan right-hand rule. How do I know my thumb? How do I know my thumb has to be pointing in this direction? Because if this is my thumb direction, this is thumb direction. I know my thumb direction has to be pointing in the way I'm indicating, because if I follow the PopCan right-hand rule law, I'm going to have my magnetic field producing more dots. So dots there and dots there. So that's my thumb direction, indicating the direction of the current, sorry. And similarly over here, this arrow is referring to my thumb direction. So you can see I am talking about this more than anything else, and for good reason. This is historically a real tripping point, but hopefully not now. But you can see you kind of have to go through a sequence of of steps here to figure out, well, okay, I'm creating a voltage, and I know this voltage will create a current because Ohm's law, and I know this current is going to start flowing, and the current itself will create its own magnetic field that tries to counteract the change. So that's a lot. That's actually saying, I mean, if you say that, if you just state what I just stated like 100 times, then it gets pretty easy to remember and easy to say, but that's a lot at first. So I'm just going to simplify this, and this would be the golden time to ask questions unless everything is perfect clear. But this induced current is traveling counterclockwise, and it's actually creating more little green dots. So there's another green dot, there's another green dot, because remember what's going on with the magnetic field. The magnetic field is going from big dots to smaller dots, and then finally it actually goes from dots to X's. So you need to counteract that. And you counteract that, nature, when I say you, I mean nature. Nature counteracts that by inducing a current. So the induced voltage induces a current that's moving counterclockwise. And if it moves counterclockwise, if it flows counterclockwise, you create dots, which is attempting to counteract the diminishing dots. So you know what I could do now? I remember my schematic convention for a battery. I could basically say, well, I know that by convention, current always flows out of the battery's positive terminal. So because I know the direction of the current flow, like this, for example, let me go back to my orange. Because I do know the direction of the current flow, I can figure out how to draw my battery. I can draw a battery that looks just like this. Positive terminal here, negative terminal here. So this would be my induced EMF. Because remember what the convention is. Conventional current, which conventional current refers to the direction traveled by positive charges. Conventional current always squirts out of the positive terminal of a battery and returns into the negative terminal of a battery. So that was a lot of talking, and we're not even done because now I have to worry about Kirchhoff's loop rule. Number 8, Kirchhoff's loop rule says for any given loop, there is no change in voltage. Do I really? I don't think I want to do the loop rule. So I don't need to do the loop rule, but I can say, aha, I now have 2 batteries. I now have 2 batteries. I now have 2 EMFs. I don't have 2 batteries. I have 2 EMFs. One EMF is the battery as shown. So you have like a dry cell battery of electrochemical device, a little 9-volt battery. And then another EMF, one EMF is the battery, one EMF is the induced voltage, or just, I'll leave it, is E equals negative N d phi dt. So I have 2 EMFs, and then should I add them together? Do they add together, or do I subtract one from the other? Here's a battery. Here's an EMF. Here's another EMF. I'm going to hire Probert. I've hired Probert, and Probert's going to stand right here. And as Probert decides to walk around this loop, that's where I was kind of thinking of making some points for loop rule, but I don't think I need to. So as Probert goes this way, I get a plus EMF from the battery. Probert then continues around the loop, and I get plus, it's not a minus, it's a plus EMF or induced. So they add together. Number 9. So my net voltage, my net EMF is going to equal the EMF from the battery plus the EMF, I guess that's induced, the Faraday's law EMF. And my battery is 20 volts. And again, I had to be really careful because I didn't know if I should add those 2 voltages or subtract them. And it turns out I add them per the last 10 minutes of conversation, plus 1.3932 volts. So I end up with a total of 21.3932 volts thanks to battery and Faraday's law.
We're going to have a look at Faraday's law of induction. For this demonstration, we've got a ring which consists of many turns of copper wire. Regrettably, it's covered with tape so they're not visible. It was known that when electricity went around a conductor, it produced magnetism. People had made electromagnets before Michael Faraday came along. If the magnet sits stationary inside the coil of wire, no electricity is made, and we can see that the meter needle is not moving. If the magnet is moved, the magnetic field within the coil of wire changes. And it is this changing.
So that's it right there. Let me just chime in for a second. I mean, what you just saw, that was it. That is a gigantic part of modern society. The fact that this magnet was moving relative to the copper coil, and then as if by magic, you get that needle on that electrical gauge moving. That is the essence of how 90% of the world's electricity is created. So let's just take another couple of minutes on this.
Magnetism that induces electricity. This is what Michael Faraday discovered. And notice that by moving the magnet in different directions, we produce electricity in either the forward or the backward direction.
So again, another interruption. That's AC. In fact, that might be good. There's more from this video, but that's alternating current. You shove the magnet, you shove the magnet forward, you get current going in what direction? In one direction. You pull the magnet in the opposite direction, you get current flowing in the other direction. That's alternating current. So again, in the most simplest way possible. All right, so here's another way to create electricity. Again, this is where you can be really creative and innovative in terms of modifying a simple approach into something more sophisticated based on your requirements. So I have a rail. I have a slidable rail. So I have this golden bar slide. So you literally walk up to this golden bar and you drag it across these two rails right here. So that would be one way. One way to generate electricity is this human power. You grab this gold bar and you drag it across these rails. And you might think that doesn't sound very efficient, but again, then you can get more sophisticated. So this little L shape device here, these are rails. So I'm going to refer to these as rails. These are my rails. And this is my bar. All right, so just for naming convention. So you or something makes this bar move upward at a velocity. And then again, as if by magic, you're going to create a voltage. So number one, part A says, what is the flux? What is the flux at 2.94 seconds? So Greek letter phi stands for flux. In this case, it would be magnetic flux. And you think of, again, amount of magnetic field going through a given area. And this is what we have to figure out. And this is the expression for flux, B dot dA. So dot products of parallels, B dot dA. So we have to figure out what B dot dA is, because that is flux and that's part A. All right, so number two, let's keep going with this. Flux equals magnitude angle version B dA cosine of theta, where theta is referring to the angle between my surface normal, which is dA, the vector perpendicular to my loop area, and my magnetic field. So you can see here, my magnetic field is coming out of the screen. So my magnetic field is coming out of the screen towards your eyeball, plus K. My dA vector, which is my surface normal vector, is again also plus K. So that's why I'm saying theta equals 0 degrees. And for sure, talk about that. I mean, right now, I'm asking the same questions, and every time I'm answering the questions the same way. Well, the magnetic field is in the plus K and the surface normal is in the plus K, but it's not always going to be that way. Especially again, check out the deep dive solutions, because I think the deep dives tackle some situations when that is not the case. All right, so right now we're figuring out flux. So I know that flux, I don't care about how things change as a function of time. My goal is to trap the spatial property. So what is B? B in terms of space, B looks to be constant. So I'm going to bring B out of the integral, because B, I don't care what B is doing as a function of time. B is constant in space. And remember, I'm not worried about time, all of time until I get to Faraday's law. This is basically telling me what's going on in space, what's happening in space. I'll get to the time dependencies when I take the derivative, which I'll do in Faraday's law. What's happening in space? B is not changing in space, so I'm pulling B out of the integrand. Cosine of 0 is once I'm left with the integral of dA. So you know what? Here's my answer. My flux is B times A. Interesting. So now, what's A? A is talking, what's A? A is the loop area. A is always referring to the loop area. And let me make sure I'm clearly identifying the loop area. Here's the loop area right here. This is my loop. And it looks like a triangle. It looks like a triangular patch. So that is my loop. So I'm shading my loop here. So I need to talk about A. And sometimes you gotta kind of drill down and be very careful how you define A. And sometimes you have to be very careful about how you capture B. But usually you have to be really careful about how you capture the correlation between B and A. And there's a few of those examples. So what's A? Well, I know that that's a triangle. So for a triangle, this is a triangle. And I know that for a triangle, area, my surface area is 1/2 base times height. 1/2 base times height. All right, so I'm looking at this triangle right here, and then I'm going to be, I guess this is my height right here. That's the height of my triangle. That is the height of my triangle. That looks better. This is the base of my triangle. All right, so there it is. There's my base. There's my height. I need to do 1/2 base times height. That looks better. And then I guess I'll just scroll this in right now. Let's see. Well, I know velocity is distance divided by time. So then I can say this distance, which in my case here is A, the height. The height of my triangle is that distance is just going to equal velocity times time. So I do know that the height of this triangle is velocity times time, thanks to kinematics. And I also know that this angle and this angle and these are all congruent. These are all the same angle. So I know that this side equals that side. So because of just basic geometry like that, the basic geometry, the height of my triangle is velocity times time, because velocity times time is distance, and distance in this case is signifying the height of that triangle. The base of my triangle right here, base. The base of my triangle is B equals, well, I know this side and that side, this also equals VT, equals 2 times VT. So I'm not writing down a tremendous amount of notes, but I am showing a lot visually. This is altitude, base times altitude. This is altitude. So this is my triangle altitude. So I'm going to make a little header. I got an expression for my triangle's altitude, and now I have an expression for my triangle's base. And again, if 45, this is a right triangle and the isosceles triangle. All right, so anyway, I'm satisfied. I'm satisfied that I did the geometry the right way. So now here's my expression for area. Area equals 1/2 times base, and base is 2VT times altitude, or the height of that triangle, which is VT, which equals V squared T squared. Okay, that's that. Number 6. So my flux. So at T equals 2.94 seconds, this is my flux. Flux is going to equal B, which is given to me, 0.459 Tesla, times A, and A is V squared times T squared, and V squared is 6.25 meters per second squared, and at time equals 2.94 seconds, 2.94 seconds squared, and we can get a number on that. And that's going to be the flux at this moment in time. And it is going to change. As time changes, the flux will change. Otherwise, no EMF. 0.459. .459. Okay. Weber. That's the units. Let me get to my notes for a second. Weber. All of a sudden we're barbecuing. But the Weber is the unit for flux, magnetic flux. Okay, there it is. Here's a Weber. Right there. So again, this is the chapter 30 notes, chapter 30 video. Goes into more detail than I'm going in, and I'm going into quite a bit of detail. But if we're defining flux the way you see here in box 3, and then we do, well, I know the units for magnetic field is Tesla, and the units for area is Tesla meter squared, so pretty straightforward. But that does add to the list of units now we have in our drawer, the Weber. All right, so let's finish this, because now we know what the answer to flux is, 154.97 Weber. But here's a question. How much voltage do you create? What's the induced voltage? So part B is saying, what is the induced voltage? And the induced voltage will induce a current, and that induced current will also create its own induced voltage. So it's like a ripple effect. All right, so here's Faraday's law. Ready? Let me make sure I'm showing something. Okay, so here's Faraday's law. The induced EMF is negative and d phi dt, and then I'll just make quick work. Ignore negative. Ignore the negative sign. Again, we'll have a whole separate analysis to figure out the direction of the current and all of that stuff. But the negative sign is basically saying, hey, don't forget to have that conversation about the direction of the current that gets induced. Ignore the negative sign, and n equals 1. You only see one loop there. N equals 1. There's just one loop. Ready? I'm just showing you one. That's one loop. So here's our induced EMF. Here's our EMF. It's going to equal d phi dt. So we know how flux behaves as a function of position, and I'm going to put that in right now. Ready, set, go. Flux behaves as a function of position d by, well, let me back up and just, okay, let me just kind of repeat the whole thing from scratch just for reinforcement. So I'm going to do, once again, integral of b dA cosine of theta. Theta equals 0 per the conversation I had a few minutes ago. So now, once again, d, all right, b does b change as a function of space? Because if it doesn't, I can bring b out of the integrand. So b does not change as a function of space. So that can go out here. And now ask yourself this question. Does b change as a function of time? And the answer is no. It's just sitting there. It's just sitting there at a constant, uniformly spaced 0.459 Tesla. And again, look how evenly spaced these green dots are. B is not changing as a function of time or of space. So I'm going to bounce out way over to there. So this is what I'm ending up with now in terms of Faraday's law. I have B times d by dt of the integral of dA, which now equals b d by dt. What is the integral of dA? The answer is a. So I just have to take b, which is given, and then do the derivative of my area function. And this was my area function. I think this was one of the biggest conversations of this entire problem is, how do you express the area? I know area is changing as a function of time. So I knew my area had to be represented with a variable t in there somewhere, because area is changing as a function of time. So that's, you're not totally in the dark here. All right, so then v squared t squared, and again, just to make sure I'm being error free, this is a, okay, that's a, thanks to this whole conversation. And I guess it's that easy. So now, and apparently I'm stringing together a lot of steps in one step. B times 2v squared t, and evaluated at t equals 2.94 seconds, and do all of that dimensional analysis. But let's see, B is 0.459. Okay. Oh, wait a minute. B 0.459 times 2. Okay. So before I run away for a break, let's talk, what's the direction? What is the direction of the induced EMF? And I'll just blurt this out in closing, because we can't have too much practice on figuring out the direction. And then I just notes to self, as time goes by, as time increases, dots increase. So that's the answer. Well, that's not the answer, but that's the setup. As time goes by, the amount of dots increase. So nature wants to do this. Nature wants to counteract increasing dots. Nature wants to counteract increasing dots. So how do I counteract increasing dots? And the answer would be to have my current flowing in this direction. That would be the direction of the induced current. Because if you use right-hand rule number 2 with this as your current direction, so this is my induced current. If you use right-hand rule number 2, or the pop can right-hand rule, and you play this game, I'm going to get X's. I'm going to, this current that gets induced is going to create X's. And so these increasing X's will counteract the increasing dots, or at least attempt to. So I know my current is flowing in the clockwise direction. You walk up to this gold bar. You go up to this gold bar right here, and you pull that gold bar leftward. Gold bar, this gold bar, you pull that leftward. And in the process of doing that, you actually will create a voltage and cause current to flow, again, as if by magic. So part A says, part A and B, what's going on with the EMF and the current induced in the loop. So this is the loop. The loop is referring to this loop right here. Let me make sure I'm, wait a minute. Okay. This is the loop, this is the current carrying loop. Okay, this yellow loop is the current carrying loop. And again, if you want to go ahead and drag that gold bar leftward, you're going to create a power source. You're going to generate some electricity. All right, so what's the magnitude of the electricity and what's the induced current? Okay, so let's do this. Let's just start off blindly kind of with Faraday's law. Faraday's law equals minus N d phi dt. And once again, it's not always going to be like this way, but it's not always going to be the case. But in this case, it can always be the case that we're going to ignore the negative. So again, the negative is just a reminder to have a whole conversation about how to figure out the direction of the induced current. But we're going to ignore the negative. And once again, N equals 1. That's not always going to be the case, but it is here and has been thus far. Okay, so now here's the induced EMF. This is the electricity you're going to generate by cranking this gold bar to the left, d phi dt, and here's phi. And I'm just going to go right to dot product representation. Magnitude angle representation, I should have said. And then, so this sounds very repetitive. The only reason I keep saying the same thing over and over again, because it's not always going to be this way. What's the angle between my surface normal and my magnetic field? Theta equal 0 degrees since my magnetic field is dots. So my magnetic field is plus k hat, and my surface normal direction is also plus k. So that's why I'm saying theta equals 0 degrees. There's my, so let me just keep reminding us, B is in plus k. Dots mean plus k. Here's my surface normal, here's my surface area. So if this gray is my surface area, my surface normal, again, I'm just going to try to draw it looking like it's in perspective. My surface normal would be perpendicular, or, tough to draw, something like that, where this would be a right angle. So this purple vector that I'm drawing is my surface normal vector, and it is perpendicular to the surface area. So that's why they're both in the plus k hat direction. Okay, so let's keep going. Seems like business as usual, but there is one big difference here. Number 3, d by dt of integral of b dA. And now, aha, here's something different. B is not constant in space. This is the first time that has happened. B is not constant in space. It's not spatially constant. B is not constant in space. Let me just highlight that word, not. It is not constant in space. And you can see that in my drawing. If I go back to my drawing, you can see that as I get further away from this wire, my magnetic field gets weaker. So I'll just indicate that as I get further away from this wire, this B gets weaker. B gets weaker as you go further away from that current carrying straight wire, which, by the way, that's the source. This is the source. This is the source of my magnetic field, source of the magnetic field. It's a current carrying straight wire. We studied that in pretty good depth. So the current carrying straight wire is creating a magnetic field. As you go away from this wire, the magnetic field gets weaker, as shown, as indicated by the green dot spacing out. So B is not constant in space. Is it constant in time? Yeah, it is. You know why? Because they don't describe any time behavior. B is constant in time. Okay, and that's a big deal. So this is very different. Not that we've dealt with B constant in time before. We have not dealt with B not constant in space. So that's good to know. So therefore, the voltage that gets created is going to be d by dt integral. And then here's how I'm going to replace B. I remember from before. I remember from like literally last week. For a current carrying straight wire, current carrying straight wire. This is a major component of chapter 29. Current carrying straight wire. I remember this. I remember B equals mu naught I all over 2 pi r. All right, so so now I know how to replace my magnetic field. I have to replace my magnetic field with something because it is changing as a function of space. So I got to do something. I have to incorporate that somehow. And this is how I'll incorporate it. Ready? It's going to be mu naught I. And I better worry about subscripts. It's going to be mu naught of I flowing through that wire. So this is what I'm going to call the current flowing through my wire, I subscript wire, over 2 pi. And I said, originally I said 2 pi r, but what is r? R is referring to the distance from probert to the current carrying straight wire. So instead of r, I'm going to say y. You know why? Because this looks like a Cartesian coordinate system. So I guess I'll just refer to, I can refer to this direction as plus x, and I can refer to this direction as plus y. So once again, that can be plus y, and this can be plus x. I mean, you don't have to do it you never have to worry about doing exactly the way I'm doing it. The only thing you have to worry about is trapping things correctly. Remember you're capturing material and geometric properties in a correct integral, an integral that captures all those properties correctly. So all of this is B. All of this is B. And then in terms of dA, here's how I'm going to represent dA. dA will be x times dy. We'll have a whole conversation on this, but right now there's integral of b dot dA. Cosine of theta equals 1 because theta equals 0. But let's have a little sidebar on dA, because I think this might actually be the trickiest part of this question. It's only tricky at first. All right, so this is my area. This is my loop area. I'm going to, again, shade it in gray. This is my loop area. It's a rectangle. What is the area of a rectangle? The area of a rectangle is length times width. So in this case, width is going to be L. So that's going to be equal to L. That's this dimension. And then what's this dimension? And that would be width maybe. So length times width. That L times that width. And this is how I would express A if it was just constant. If this was just a static loop, it wasn't changing as a function of time. But now it is changing as a function of time. So I think since as time increases, I'll say, as time increases, I could say, well, the area is going to equal L times W. Here's how I'm going to write W. I'm going to write W as X. So, in fact, just to avoid a little bit of confusion, I'm not changing anything, just the order. So the area of this gray patch is going to equal W times L. Same thing. So that's true if time is not changing. That's true statically. As time changes, as time increases, I'm going to replace this W variable, which is referring to this dimension right here. Instead of calling it W, because it's not constant as time changes, I'm going to call it X. And that's why I drew my X axis the way I did. All right, so now what about L? L seems to be constant, but you know what? You know what I'm going to do? You could argue, well, L is constant. Just write it down as L. I'm going to write it down as dy. L times dy. Why am I doing that? Why am I differentializing L? Because L looks like a constant. And I'll call this A, B, C, D. So L becomes dy because B depends, or B is a function of Y. B is a function of that Y dimension. That's why. So that's why, again, I'm not using L anymore. I'm going to call L dy because I want to make dy my variable of integration. Let me add that. That's, I think, sounds good. I want dy to be my integration variable. Why do I want dy to be my integration variable? The answer is because B depends on it. Because my magnetic field depends on it. Okay, so that is a very long-winded conversation just to talk about why I'm going to represent area as X times dy. And that, to me, that's tricky. That's tricky. We could talk about that a lot more. But it's once you really see it, once you see the forest through the trees, then you can handle any situation. You can handle this situation or a much different situation because you kind of know, again, what you're trying to tie together. So step number 5 is number 5. Okay. Well, I have a lot of constants. I'm just going to bring all of the constants out. Let's see. Mu naught is a constant. The current going through the wire is a constant. 2 pi is a constant. So those can come completely out of the differential and the integral. Mu naught I wire 2 pi. All right, so now what's left? D by dt of x dy all over y. Okay. So and I forgot my integral. D by integral. I forgot my integral sign. Integral of x dy over y. All right. So what do I do now? Does x change as a function of x is not part of my integral. So x is not part of my integral. So the question is, I mean, that's clear because my variable of integration is y, dy. Now, do I bring x out to the left of my integral or do I bring it out of my differential? And I bring it out. I don't bring it out of the differential. I just bring it out of my integral because x does change as a function of time. You can see it. You've grabbed hold of that bar and you're dragging that bar leftwards. So this is what's going on. Now, number 6, the voltage that you create is going to equal mu naught current flowing through the wire all over 2 pi dx dt integral of dy over y. And we'll worry about boundary conditions, I guess, kind of now. So I get mu naught IW all over 2 pi dx dt is v. So there's my velocity, because I was kind of worried about that. I kept thinking to myself, where do I include the velocity information? And to be honest, that I use that as guidance. I'm thinking velocity, this depends. This whole situation depends on velocity somehow. So because it's rate of change of flux, and velocity is a rate. So that actually, again, kind of kept reminding me, it kept me looking in a certain direction, saying, well, I gotta capture velocity somehow. And this is how I capture velocity. And the integral of dy over y is natural log of y. But let's talk about boundary conditions. Now, I need to so I'm basically going to say, hey, integral calculus, I would like you to take all of these elements starting out here and, going all the way to L plus A, and then integrating, gluing them all together until you get to A. And then that's what I'm going to do. So my variable of integration would be from L plus A all the way down to A. So this would be integral of L plus A minus, not integral, natural log of A. And I guess that's it. So it's not it, but now at least we know the voltage. Mu naught I flowing through the wire over 2 pi natural log of L plus A over A. Do we know all of this? Do we know L? Yes. Do we know A? Yes. We know everything here. Do we know current going through the wire? Yeah, we do. And we know V. All right. So let's get the answer to part A. 1 down, 4 to go after this in terms of this quiz. Times I. Okay. That's the answer to A. Let me see. Sanity check.
I have a quick question. So is mu supposed to be the 4 pi times 10 to the negative 7?
Yeah, that's correct.
Okay, and everything should be in meters, correct?
Just be dimensionally consistent. So yeah, you have to worry about, meters and kilograms and seconds and okay, let's see. All right, let's continue. That was part A. Part B says, what's the current? So here's part B, number 8, number 9. Part B says, what's the current? Now I'm going to write that down. I induced. So again, if you create a changing flux, it's not enough to have flux, which is magnetic field over the area. You have to have changing flux. But if you go ahead and change that flux, you will induce a voltage, and that voltage will induce a current. And here's the question now as well. If you get this much voltage, how much current gets created? And this is a job for Ohm's law. Ohm's law says V equals IR. So I equals V over R. And in our case, this V gets created. This is an induced EMF. So it's going to be whatever that EMF is. For me, it was 141 and some change microvolts over R. And do you know E because you got the answer to part A correctly. Do you know R? You do know R because it's given to you. It says the rod has a resistance of 0.358 ohms. The rest of the loop has negligible resistance. So this is going to go quickly. You take your correct answer to part A, which is your voltage, and divide it by the resistance. This is, again, Ohm's law, 0.358. And you're going to get some amount. You're actually going to get quite a bit of current. So just by moving that rail, you've created some current because you've created some voltage. I get 3.96 E minus 4 amperes equals 0.396 and some change milliamps. So that was pretty quickly, and that was part B. Okay. Done with A. Again, A, we figured out how much voltage we're going to create. B says, well, if we get that much voltage, we're going to have some charges moving, and we get charges moving to the tune of 0.396 milliamps or whatever your number is. Part C says, at what rate is thermal energy generated in the rod? This was a job for power. So electrical power, remember what power is. Power is the rate of doing work. I can write it like that. Or power is the rate of consuming or producing energy. In the case of a resistor, because basically this bar behaves like a resistor. So I'm going to draw the schematic symbol for a resistor. In the case of this resistor, from chapter 27, we had 3 ways to express power. So for electrical circuits, for a resistor specifically, for current flowing through a resistor, it was I squared R. And I squared R is the rate of thermal energy dissipation. What do resistors do? They impede the flow of current. What happens when you do that? You generate heat. So I squared R is the rate of thermal energy dissipation. So all you need to do is take I squared R. And then we're going to be done with that. So this is the answer to part C. There's I squared times R point something or other, 0.358. Okay. So this is how much heat gets generated as a result of current flowing through that bar, which has a resistance, 5.62 E minus 8 watts equals, they want it in microwatts, so move it over 2.0562 microwatts. And this is the answer to part C. So part B and C is literally plug and play. Part A was some heavy lifting. Part B and C is just plugging in. Part B was Ohm's law. Part C is just I squared R heating. Part D is now asking, what is the magnitude of the force that must be applied to the rod to make it move at a constant speed? So that gets a little bit deeper. I'll write over here. So now we're on to part D. Step 14, I'll change colors. What is the magnitude of the force? Part D. The magnitude of the force. So let me erase this. You are walking up to this golden bar. You're walking up to that golden bar. You grab hold of this golden bar and you're apparently pulling leftward like this, leftward. So this is the force that you applied, F. This is the force that you apply to that bar. You're pulling it to the left. It's moving to the left. And now the question is, what's the magnitude of that force? What D says, what is the magnitude of this force that you apply to move at a constant speed? Okay, so you know what? Let's talk about what is the direction of the magnetic force on this gold bar? So this is a job for flat hand, right hand rule. All right, number one, flat hand, right hand rule. And again, what am I looking at now? I need to figure out what is the magnetic force acting on this gold bar. So we're going back to chapter 29. This is a current flowing through a straight wire exposed to a magnetic field. So I need to do my flat hand, right hand rule. Flat hand, right hand rule means my fingers are pointing in the direction of the magnetic field. That's right. And my thumb, this actually, well, okay. What's the direction of, I guess we have to back up. What's the direction of the induced current? So same, put a pin in that. Right now, we're talking about the direction of the induced current. So let me just make a little sidebar here. As time goes by, get more dots. Dots increasing. Dots increase. As time goes by, the dots increase because this bar slides from right to left. The dots are increasing. So the induced current needs to counteract this. So what's the direction? What does the current direction need to be? So I'm holding my pen. My pen is representing that gold bar. And if I want to create X's, the only way I can create X's, which I do, I need to create X's because dots are increasing. So this is going to be the direction of the induced current. Ready, set, go. That's the direction of the induced current. So the current's going to flow like that and like that and like that, and so on and so forth. So that is a critical piece of this puzzle. This is the direction of the induced current. It's going upward. And again, I'm just going to double check that. Not yet with that. I'm going to double check that because if I'm using my right hand rule, my thumb's going in the direction of the current. So my pop can right hand rule, if I'm applying it correctly, is showing that I'm going to be, I am in fact going to create a magnetic field that's flowing into the loop, like what's a good color? Like this, already there. So that's going to be an X. And then play that same game here. That's going to be an X. So that's the only way I can create X's, which represent magnetic field lines going into the screen or into the page, or minus K, is if the induced current is flowing up. So now do your flat hand, right hand rule. Your fingers are pointing in the direction of the magnetic current. Your thumb, look at that. Look how comfortable this looks. But my fingers are pointing out of the screen. My thumb is pointing up. So let's just add that as commentary right here. So flat hand, right hand rule. says that my fingers are going to be, my fingers fingers out. Fingers from flat hand rule plus K out of the page. My thumb is up. Thumb is up. My palm is facing to the right. So this is the direction of my palm there. So that's the direction of the force that you need to counteract. This is my palm direction. My palm is facing that way, and this is F sub B. Okay, so that was a lot of conversation just about directions, but all of that was good. That's the heavy lifting. All right, so I need to perfectly counteract that magnetic force. So specifically, step 13, step 4, I'm over here, step 14. Okay, so I know what that force is. I know the force going through that bar, the magnetic force going through the bar, the gold bar. I know that generically. I remember IL cross B. And then I'll go straight to magnitude angle format I. And I better worry about subscripts here. This is I going through the bar. So what did I call that? I guess I just call it bar. This is the current going through the bar as opposed to the wire. So IL cross B, or magnitude angle, is B cosine theta equals 0. Although, let me just point out, theta equals 0 because theta is referring to the angle between the magnetic field lines and the current vector, the length vector, I should say. And let me just show that over here, just so nothing is left to the imagination. Okay, so I will draw my length vector. My length vector will officially look like, did I draw that current going up or down? 8, 9, current's going up. All right, so current's going up. So that tells me the direction of my length vector. So in that expression, IL cross B, L is referring to this. This is L. This is my L vector. It's in the same direction as the current. So this is my L vector. And you can see my L vector is perpendicular to my B vector because this is representing my B vector. There's vector L, there's vector B, referring to this dot, which is coming out of the screen. Okay, 90 degrees. All right, let's keep going. 15. So now here's a, wait a minute. B varies as B varies in space. V varies in space. So I just can't plug in numbers. V varies in space. I'm going to have to do the integral thing. I'm going to say the force that I apply to that bar is going to be the opposite of that magnetic force, opposite and equal. If it's opposite and equal, it means it's going to keep moving. It doesn't mean it comes to a stop. But if I apply an opposite and equal force, it's going to move at a constant speed. And I better do, and I'm just going to deal with magnitude. So the magnitude of F subscript B is going to be, and I better jump into integral calculus. I need to do the integral. And why am I doing this? Because again, V varies as a function of space. So this is a job for integration. So I'll say this. that magnetic force is going to equal the integral of ILB, I of the bar, L times B. Okay, so we're kind of back in a similar situation. So it's going to be a little bit different. All right, B. So we talk about what is B again. So here's B again. We know this from before. I need to take the integral of I going through the bar. And can I bring that to the left of the integrand? That's going to be the same everywhere. All right, so that can come out of the integral. I can come out of the integral. Now here's the question, can L, and I don't think it can, L cannot come out of the integral because there's an intertwining or a correlation between B and L. So I'm going to leave that in the integral. And I'm going to change it to dy. Once again, I'm going to make L my variable of integration. And here's B. B equals mu naught I wire over 2 pi, the distance away from that wire. There. So just some notes here. Because this is the fine print. Why did I go from L to dy again? I'm going from L. I'm replacing L with dy because I need to, find how B varies according to Y. That's my motivation. So I need to find out how B varies as a function of Y. So that's why I'm making this my variable of integration. This collectively is, again, this is the magnetic field created by a current carrying straight wire, which was generically mu naught I over 2 pi R. So just personalized for this situation. All right, so step 19. Step 19 says my magnetic force, which I have to counteract, is I can bring all of these constants out. So there's mu naught IB going through the bar all over 2 pi. Any other constants? Yeah, there is. I of wire times natural log of Y. And my same old boundary conditions. Boundary conditions would be, I got to go all the way out. I'm going all the way out to L plus A and gluing together all of those elements all the way down to A. So this is the force that you have to apply to just perfectly counteract the induced magnetic force. Mu naught I going through the bar, I of the wire, everything is known here, over 2 pi, and then this ln again. Okay. Okay. That's the answer to part D. And just a note, I need to exert this force. I need to exert this force to move bar at a constant velocity. Okay. Last question. At what rate does this force do work on the rod? So there's a few different ways. There's a few different ways to answer this, but 22 is part E, and it's saying how much work, what's your power? So this is saying what power do you exert? That's the dollar sign. So here's a way to think about this. Power that you exert is equal to the force that you exert times the velocity. This is one of the many expressions for power. Over here, if I kept going with this in step 12, another expression for power equals force times velocity. So you're going to get the right answer doing that. Or you know what? This equals, you could also just say I squared R equals same as rate of heat dissipation. Same as rate of heat dissipation. The only reason you need to do work per time, which is power, the only reason why you need to cough up some power is because some energy is being lost to heat dissipation. Otherwise, if there was no heat, if there was no energy lost to heat, you wouldn't have to do any work. You would just basically nudge that rod to get it started, and then away it would go. But and we already know what I squared R is. I squared R is the thermal energy dissipation. We already figured that out in part something or other. We figured that out in part C. So this equals part C. And either way, force times velocity or I squared R should get you the same answer. Part C said I squared R, which is the rate of heat dissipation, which is the same as the rate of you doing work or power, was 0.0562 microwatts. And then we're done with this problem. Completely done with part E. So this is a long problem. But one of the key takeaways here is this was a situation where the magnetic field did not stay constant as a function of position. And then again, one of the problems, maybe it's the next problem we're doing, or maybe it's a deep dive solution, talks about situations where the magnetic field is changing as a function of time and space. So keep your eye peeled for that. And that is it for this. This was the answer to part E. Okay. All right. One more. It's now 3:35. Let's do one more. Chapter 30, quiz 5. Okay, you should now see Chapter 30, Quiz 5, our last quiz for today. Give the old read through. Okay. This is pretty interesting. You take just a loop of wire. I mean, we could do this right now. You take a loop of wire and you drop it. We're ignoring air drag. We're ignoring air resistance, which probably would be pretty small. But we're ignoring air resistance. But even though there's no air resistance, this will reach a terminal speed, meaning that even if there's no air resistance, even if you did this in a vacuum, this loop would eventually just stop accelerating and move at a constant velocity. That's what terminal speed means. Maybe you've heard that in conjunction with like jumping out of a plane with a parachute. You jump out of a plane with a parachute, you start to speed up as you fall towards the earth, but eventually you stop speeding up, you stop accelerating because your air resistance kind of draws even with the downward pull of gravity. In this case, there is no air resistance, but this downward pull of gravity is being offset by, that has to be a magnetic force. So I know there must be a magnetic force, and I know it must be oriented upward because terminal speed means the sum of all forces equals, well, I've got the magnetic force going up, and then I have the weight force going down. Newton's second law says mass times acceleration, and acceleration equals 0 if terminal speed is attained. So if delta V equals 0, it means constant velocity. It means constant velocity means no acceleration. So that's how I'm quickly saying, well, that magnetic force that arises has got to be opposite and equal to the gravity force. And then the question is, what is the terminal speed? So somewhere in step 3, there's got to be a velocity variable. All right, so let's talk about, first of all, as long as we're here, flat hand, right hand rule. Fingers go in the direction of the magnetic field, which is going into the screen. Got it? Thumb goes from left to right because my palm is going up. So you know the direction of the induced current, even though it doesn't ask us this. I mean, it could on exam 4. But you know for a fact that the induced current has to be going in that direction because of the flat hand, right hand rule and everything we know. So this is the induced current going from left to right. Let me just double check that. Did I do that right? Flat hand rule. I've got magnetic field lines going into the page because they're X's. Thumb, if the thumb is going to the right, it's because my palm is pointing up, which my palm needs to be pointing up. All right, that's all good. So number 4. Well, I know for a current carrying loop, F subscript B equals IL cross B. So here's another IL cross B. And actually, you know what we should do? Because what if I almost forgot to do the following? I know this is my induced current going in this direction. because it's just a single loop. So draw my induced current apparently is going clockwise. I am not gonna draw the current going down here. Well, I guess I could, but it's not exposed to a magnetic field, so I don't care about it really. But if I do my right-hand rule, my flat-hand right-hand rule, I should say, if I once again do my flat-hand right-hand rule, let's see, current going up, fingers in, I've got F sub B going this way. So, there's another F sub B. It's going to the left for this segment. F sub B is going leftward for this segment. And I'm going to play the same game again in, how do I do that? Thumb going down. Okay. So if I do my flat hand, right hand rule for this right segment, so maybe I'll call this FB subscript right and FB subscript left. So that's noteworthy. Can't sweep that under the rug. I'll just say FBL equals FBR. So they cancel. They don't make a contribution. Only that upward oriented F sub B makes a contribution. So back to number 4, number 5, F sub B equals ILB sine theta. We have to worry about theta. What is the angle between my B vector and my L vector? Well, for the top segment, which is the only segment I care about, this is my L vector. This is vector L right here. It's in the same direction as my current. Okay, so number 6. So that magnetic force that arises equals ILB. Do I know? I know B. I know B. It's given, right? Yeah, 0.78 Tesla. I know L. L is given 0.19. So I know L. Do I need to worry about? And those are constant. So I don't need to worry about. B is constant. B is constant in space. B is constant in space. I is constant in space. So, okay, so number F sub B equals I. Now here's I. Ready? I is Ohm's law. The current is going to be expressed as I is Ohm's law. So E over R times L B sine theta. So let me just develop this because this was Ohm's law. Ohm's law says V equals IR. So therefore I equals V over R. And in our context here, V is that induced EMF. Okay. So now I guess we turn our attention to figuring out the induced EMF. All right. F sub B equals, well, you know what? Instead of, I'll drag it all along, I guess. Here's the induced EMF. Ready. It's going to be negative N d phi dt. All of that is my EMF. Script E. All over R times L times B, and theta is 90 degrees times sine of 90 degrees. Okay. And then once again, for the umpteenth time, let's ignore the negative and N equals 1. We're ignoring the negative and N equals 1. Okay, so let's keep hammering on number 7, number 8. That magnetic force is going to equal my Faraday's law, d by dt of integral B dot dA. And this is where we have to start thinking again. B dA. Oh, and look, here's another dot product, cosine of theta. Okay, so all of that. This is my EMF. All right, so as mentioned, the magnetic field does not vary as a function of time or space. So this magnetic field right here can come out of the whole shebang. It's not a function, doesn't change as a function of time, so I don't need to differentiate it. Doesn't change as a function of position, so I don't need to trap its dependency on space via that integral. So that's why it's coming all the way out. And then how do I express A? And so this is another deep conversation. So this area right here, what's a good way? Well, I know in general, area equals width times length. Again, that would be true if things were static, but it is changing. So in this case, I think A, so if this is width, let me erase some of this stuff since I can't remember. Okay. All right, so this area here, what's a good way to represent this area so that, again, and it traps any B dependency, but there's no intertwining, there's no dependency on the magnetic field and the A. So again, because the B came all the way out of the differential and integrand. So I think that L is a constant. So the only thing that is going to change, I believe, is just going to be this Y variable right here. So this is my Y variable. So I'm going to call that L times Y. So now let me just make sure that makes sense. And I'm keeping like my eye on the interdependency between the magnetic field and this dimension, and there is no. So I don't have to worry about making that my variable of integration. I don't need to worry about I don't need to call LX. I don't need to make this assignment. So I don't need to do that because that's not a variable. That is just a flat out constant L. So I don't need to do that. That's why I am keeping this as variable L. And then what is changing is this dimension right here. That dimension is changing. And as that dimension changes, how do I represent it? I'm just going to represent it as a Y. Maybe should I call it dy? No, I don't have to call it dy because I don't need to use it as a variable of integration. All right, so let's go. Number B times d by dt integral of dA cosine of theta is 1. All right, so that becomes B. Oh, and I forgot the other things there. Times L times B all over R. Yeah. Did I forget L times B over R? I think that's good. All right, so number 10, this magnetic force equals B times the integral of dA is a dA dt times L times B all over R equals B. And if this is A, then dA equals L dy. So this is going to be B times L dy dt times L times B over R. So let me just, dA dt is L dy. So this is dA dt. Okay. And then this becomes number 11. The magnetic force is going to equal B squared L squared V over R. So that's that. That's my final expression. I know everything there except for V, and that's my dollar sign. And I do know, again, that this magnetic force, which is oriented upward, once again, all of that conversation is needed to explain why. And worry, some of you need to worry a lot more about explanatory comments, but you need to provide all of the explanation, show all of the work to show why. That is F subscript B, which equals the upward magnetic force is equaling the downward gravitational force. And then number 12, solve for V, because you know everything. You know everything in statement 11 except for V, and that's what you're solving for, and that's the terminal velocity. And that's it. We're not going to watch the whole 10 minutes, just a chunk of this.
So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so is adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now, the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer, and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually, the inductor provides nearly no resistance, and so the electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy.
Check this out. You guys know what this is. You've seen this. You know this is a speaker. If you've taken off the covering, you've seen these before. On the very top, that's called a tweeter. In the middle, that's called a mid-range. And at the bottom, that's called a woofer. And this is just an empty cavity, an empty hole, basically. So this top tweeter handles the high-pitched sounds, the high-frequency sounds The mid-range handles the stuff in between, and this woofer handles the bass sounds, the low frequency sounds. And the thinking is, if you can figure out how to send the high sounds up top and the mid-range sounds to the middle and the low frequency sounds to the bottom, you get a better dynamic response. You get a better sound, basically. It sounds more richer. So this is a good example of signal filtering. And I'm bringing up filtering because we're spending the rest of today talking about RL circuits. R for resistor, L for inductor, RL circuits. That's all day today. And they're used in, among other applications, filtering. So then the question is, if you're listening to music, how do the electronics figure out how to send the high frequencies to the top, the mid frequencies to the middle, and the low frequencies to the bottom? And the answer is filtering. So here from our friends at Falstad, this is a simple filtering circuit. What's the name of this? I think that it's just a well, I always think of this as just a speaker filter. So you can see here on the left screen down here, this is the low. In the middle, this is the mid-range, and on the right, that's the high range. Watch what happens when I restart this simulation. I'm just going to click reset. Ready? 3, 2, 1, reset. And then you see my AC source is starting at 140 hertz, 200 hertz. So I'm going from low frequency to high frequency. And now you see this middle graph start to wake up. This is the mid-range. And the graph on the left is the woofer. That's starting to die out because I'm getting mostly mid-range frequencies. And again, keep your eye on this AC generator. Now I'm at 1500 hertz. And then all of a sudden, you're going to see the graph on the right wake up. That's the high pass filter. So you can see this is just a great simulation because it's actually showing you the portions of the circle that are activated based on the frequencies that they encounter. So here we are. I'm driving this at like 15,000 hertz. So the low pass filter doesn't capture anything. The mid-range filter doesn't really capture anything. And it all goes through to my high end or my high frequency tweeter. So again, just one more time, not in its entirety, but this is it. You see on the left, that's my woofer. Those are my low frequency sounds. In the middle, I'll speed this up a little bit. In the middle are the mid-range, and then on the right, the high frequency. So this is all done. If you look at the schematic, you see an AC source, and then you basically see capacitors, resistors, and inductors. So with that, you should be able to now go into Chapter 30, Quiz 6. And again, today is RL Circuit Day. So this is sort of the flip side of Chapter 30. So the first part was all about Faraday's law, Lenz's law, electrical generators. And today is all about RL circuits. And just some more perspective. This is the march we're on. We are following this path. Again, just to give some hindsight, we technically talked about RC circuits, although to be honest, we didn't hit RC circuits normally as hard as I hit them. And that's because of the hybrid nature of our course kind of prohibited me from doing this as a lab. But RC circuits was chapter 27. RL circuits is chapter 30. Then you have something called an LC circuit in chapter 31. And then the ultimate destination is an RLC circuit. This is the subject of our last lab, RLC circuits. And this is in many ways AC. This is the study of alternating current. And we live in an AC world because DTE energy and consumers power and all these other power generation plants generate electricity with spinning magnets or magnets spinning around an electric field. So we live in an alternating current universe or society, I should say. And that's what we're going to really kind of get more acquainted with via RLC circuits. So that's a little thumbnail on where we are and where we're going. Give this a read. Give this a read through. I'll be quiet for a moment. Okay, I'll get started. All right. We're given this circuit. We know the value of the resistor and the inductor and the EMF. And then we have a fuse here. And it says this is how this fuse works. It can accommodate up to 1 ampere of current. So if it's accommodating anything between 0 and 1 ampere of current, this fuse right here behaves like a wire. It has 0 resistance. So it's completely benign for currents up to 1 ampere. But if the current exceeds 1 ampere, then it blows. Then it literally melts or flips. You can have some fuses literally melt, and you have a circuit opening. Other fuses basically just switch. They click like a switch, like a light switch from on to off. So we can accommodate up to 1 ampere of current. If the current reaches 1 ampere, the fuse blows and thereafter has a infinite resistance, which is infinite resistance means it's like there's an opening. This is a gap. The bridge is out. Switch S is closed at time equals 0. When does the fuse blow? All right, so if I close this switch right here, switch S, if I go from open to close, then I've closed a circuit, and then I'm going to ask myself, what's going to happen? And I guess I'll use Kirchhoff's voltage rule, Kirchhoff's loop rule. Sorry, I'm thinking to start with KVL. Okay, number one. Here's KVL, but even this is kind of tricky. What are we going to use as our loop? So as soon as I close this switch, I'm going to have current, conventional current, which is the direction taken by positive charges. And by convention, conventional current flows out of batteries or in EMFs. By convention, current flows out of the EMF because we actually have 2 EMFs. We have the battery EMF and then we have an inductor EMF. So as soon as the switch is closed, the current's going to flow. And then the question I have right now, what's it going to do at this junction? Here's junction, let's just call this is junction J1. Does some of it go up and some of it turn to the right, or does all of it turn to the right, or does all of it go up? And the answer is all of it goes up because as long as I'm operating at less than 1 ampere, this is basically just a wire. So nothing goes through the resistor. Nothing goes through the resistor. So I'm just going to draw my current going north. All right. Fine. And then it goes through the fuse. And again, at this point, the fuse is just like a wire. And then it's just making its round trip. And none of this is going to go through the resistor, because why would you go through the resistor if you could instead go through a straight wire? So this is my circuit. I go through, here's my switch, here's my inductor. All right, so this is my loop. I'm going to draw my loop as in my Kirchhoff's loop rule. Let me fix that too, but right, here's my loop. So there, this is my loop. And let me officially write this down correctly. This is Kirchhoff's loop rule. Kirchhoff's loop rule says that delta V equals 0. So you know what I have in this loop? I've got plus EMF. I'm climbing up this battery. So Probert starts here, goes north as indicated by my red arrow directions, my red direction arrows. Goes through the fuse and then goes through the inductor. Now this is where we got to get careful, because inductors have inertia. And this is really why I started with that video. Inductors will create a voltage, which is cool. You're thinking, hey, We like inductors. We like solenoids because solenoids create and store magnetic fields. And who doesn't like magnetism and who doesn't like magnetic field energy? The answer is we all like magnetic field energy. But the Lenz's law aspect comes in as follows. If you try to push current from left to right through the, from right to left through the inductor, like we're showing here, the inertia of the inductor will do the following. It's saying, well, okay, if you push me, I'm going to try to push back on you. So we need to draw a resistance current. So this is going to be what the inductor tries to do to the current. So we could even label this induced current. This is an induced current. And it's trying to fight the current going from right to left. So because that's the response of this inductor, we can stay true to our EMF labeling scheme, and we can call this side is going to be plus, because by convention, current always goes out of a positive side of a EMF and comes into the negative side. Just like with this battery, again, if you look at this battery, the convention is consistent. Current emerges from a positive terminal and flows into a negative terminal. Same here, as far as the induced current flows out of a positive terminal and into a negative terminal. And you could actually think of an inductor as looking kind of like this. If you wanted to draw like a battery schematic, this is what the inductor looks like, at least at first. So if we're sticking to our Kirchhoff's loop rule, Probert encounters a voltage increase, an EMF increase, goes around this loop, encounters the inductor, and that would be minus VL equals 0. And then I should label this maybe VL. VL is the voltage change across the inductor. So this is V subscript L. So it's important to know that this is an EMF, V subscript L. This is an EMF, which means we do have to label it correctly. It's an EMF just like this is an EMF over here. So we have two of them. All right, so there's my loop rule. So I'm just going to keep running with that because we are trying to figure out at what time does this fuse blow. So number 2, I have my EMF equals VL, which means my EMF is going to equal L di dt. And this is in your green sheets. We should have covered right here. Let me put my green sheets on the screen just for reference. But there is my inductor voltage right here. Let me take a snip of this. So this is ripped from the chapter 30 green sheets. I'm just going to take a snip of this, but again, you would be, I think, very well served if you go through and understand this whole background and derivation. So I always cringe whenever I do what I just did, when I just sort of paste, the one equation, because I'm always paranoid about just trying to solve problems using equation hunting, like not think about what's happening, just scan for equations. But anyway, having said that, there's the equation. Crossing my fingers that, again, you go through the backstory. So let's process this. Oh, this negative sign is still Lenz's law. This is still basically Lenz's law. Lenz's law means, hey, it's going to fight. It's going to basically inductor resists chain I'll leave it like that. The inductor resists change, hence the term inertia. What's the definition of inertia? Inertia, mass inertia is basically a resistance to an acceleration. So if you have a gigantic, heavy steel wheel that's spinning at 100 RPM, it's going to take a lot of effort to slow that down, just like it would take a lot of effort to speed it up if it was sitting there stationary at 0 RPM. So this is it. This is what the loop rule hath wrought. Pretty simple. So we got to go from number 2, and that was a good point. That is Lenz's law. We got to go from number 2 to get the answer. What's the how long does it take for the current to grow to 1 ampere? And we have that right here. There's I, so it's living. We see the dollar sign. The dollar sign's here. That's not I, it's differential I, but let's see what we can do. Number 3, the EMF equals, well, maybe we'll do it like this. I'll multiply both sides by dt. So we saw this yesterday. E dt equals L di. So we're just in basic calculus, the basic calculus land. So I would say I is going to be a function of t, and it's going to equal the integral of di from some initial t to some final t. So if we're taking the integral of di, let's take the integral of EMF over L, because apparently I'm moving the L from here to here. From here to here, okay, times integral of di. Come on, okay. So then we have to worry about, I'm just going to leave this as an indefinite integral right now. So the current, which is a function of t, equals EMF over inductance times I. Except I made a mistake over here. Let me fix this. Sorry. Typo alert. So I have dt. So I got ahead of myself. Okay. I'm just thinking differently. All right. dt, so let me erase a bunch of stuff. Because I wasn't looking at the question. For some reason I was thinking we have to figure out what I is, and we know what I is. We have to figure out when does t, what's the value of time at which current grows to 1 ampere. So let me kind of restart. Number 4 says dt equals L over epsilon di. So if I integrate both sides, integrate that side, integrate that side. So I have t equals L over epsilon. I got to fix this some more. Of di. Okay. So t equals L over epsilon, L over E di plus some I, geez, plus some constant. Okay. All right. So number 6, at t equals 0, I equals what? What does I equal at time equals 0? So the instantaneous response, meaning the transient response or the instantaneous response, when you close this switch, current will instantaneously flow from the EMF to the inductor, but that's where the instantaneous part ceases, because as soon as this instantaneous current, it literally turns on in the blink of an eye. As soon as you flip the switch, current flows immediately to the inductor, but that inductor has, at the very beginning, it has a tremendous amount of resistance. So at the very beginning, at t equals 0, I going through the inductor equals 0. So right at the very beginning, there is no current flow. So that's how we get the answer to what is our constant of integration. All right, and I guess that's kind of mangled, but I guess that's good. All right. So anything else? Are we good? Mm-hmm. All right. Let me bide my time. I'm looking up something while you're fixing that or finishing that. Oh, well, no, I think we're all good. I was going to say, do we know all of those values? And I think we do. My inductor is given. My EMF value is given. And then what's I? I equals, for me, 1 ampere. Because as soon as I exceed 1 ampere, it's game over. So it boils down to a very simple solution. Okay.
Wait, I'm still a little bit confused. Do you think you can walk us through all the way to the fuse blow part?
Again?
So the question is, when does the fuse blow? And I'm understanding how to get the current, but I don't understand how to get the time that it blows.
Oh, blows at number 5. So basically the question is, when the switch S is closed at time equals 0, when does the fuse blow? And the fuse blows at I equals 1 ampere. For me, you might have a different number. So here, this current value right here is 1 ampere for me. So this amount of time passes for the current to go from 0 all the way up to 1 ampere. If that answers your question. So, I mean, this is an exceedingly simple final expression. It doesn't help that I was kind of choppy and making a bunch of missteps along the way. But to me, you're going to get, this is your answer. I mean, again, if you don't have the right answer, your answer is L times I over the EMF, where I is the current at which your fuse blows. So again, here's your answer. If you wanted to ignore everything and just punch in those numbers, you're going to get the right answer. But the real takeaways is all of the stuff that came beforehand. The real takeaway, in my humble opinion, is understanding why this is a positive terminal and this is a negative terminal, and how EMFs will always fight change. And yeah, I mean, this is a good example of how a fuse behaves. So and then we use the loop rule, Kirchhoff's loop rule. So good stuff here. Even so, I'm hoping we got a lot of substance out of this, even though at the end of the day, all you need to do is say L times I divided by epsilon. So let me move on to quiz 7 and ask more questions, especially since, again, I know I was being less than eloquent. All right. So here comes quiz 7. All right, you'll see it right now. Quiz number 7. This is an RL circuit. Another one. Okay. Here's our question. Suppose this EMF varies with time so that the current is some function. All right, so if I go into Desmos, if I just graph this, here's my current function. So if I should do for x greater than 0. I'll leave it like that. So we have this current function that is just brought to you by a sophisticated EMF. 1.5 plus 6t is my function. Okay. We know the value of the resistor and the inductor. Find the EMF required of the battery at time equals 6.0 seconds. This is where I'll go back to my green sheets. And again, this is on sort of the other side of chapter 30. The first side was all about Faraday's law, Lenz's law, and generating inductance. The flip side is this stuff, is RL circuits. So this is very analogous to RC circuits, which we had a few homework problems on that. Normally you have a very robust lab, and but we didn't see the lab part, but we'll see the RL part. So here's the section, the RL circuit section. This is the fundamental derivation of the expression you see in box N like Nancy. And this is all based on the loop rule. So this is what happens when we apply the loop rule and a few other tidbits to this circuit you see in the top right. We're throwing the switch from B to A, and we're closing switch S1, and we get a response. So anyway, I'm going to take a snip of this. Box N is what results when we fight the good fight and apply Kirchhoff's loop rule to that RL circuit. All right, so I'm just keep this here as reference. So the question is, you turn on, you flip the on switch. This battery is producing this current that looks, again, that graphically it looks like this. And apparently it starts off at 1.5 amperes. So maybe that's worth keeping in mind. All right, find the EMF of the battery at t equals 6 seconds. All right, so step number 1. This is an RL circuit. This is an RL circuit because I have a resistor and an inductor. And I would even go one step further. I would say this is, let me do this. This is a charging inductor. Okay. This is an RL circuit with a charging inductor. Okay, so again, if I just go back to my green sheets here, notice this header here says charging inductor. So this expression that I copy and pasted that you see in box N, that's showing the current behavior for a charging inductor. And then if you kept going, there's another section titled discharging inductor. What happens if that inductor is losing magnetic field energy? Okay. All right. So let's go through this again. Well, I might fight the good fight for a little while longer. Number 2, I'm going to do my loop rule. So here's a loop.
You need to switch the screen.
Oh, thank you. I'm going to go back to Kirchhoff's loop rule. Which says plus EMF. Got to worry about conventions here. This is going to be a plus, and that's going to be a minus. You should be familiar with that now. Resistor terminal conventions. If current is entering my resistor in this like this, then that's the positive terminal. That's the negative terminal. What about my inductor? Remember what inductors do, and they kind of actually show you. They give you a little heads up, like, hey, remember, inductors don't like to change. So an inductor will fight change. So this is not helping current flow. It's actually hindering current flow. So this would be a positive, and this would be a negative. Which means, again, you could think of this as a battery. With that as the positive terminal, that as the negative terminal. There is a voltage drop across. So maybe I'll just write it like this. The EMF associated with this inductor equals negative L di dt. And let me just add this too. When you see this negative, which is Lenz's law, and you see this di dt, if you just look at that negative sign in di dt, you can, from that you can get, once again, inductors hate changes in current. That's what the negative sign means. That's what DIDT. It's not saying inductors hate current. It's saying inductors hate changes in current. So that seems like it could be a helpful comment. All right, so I'm back to my loop rule. Minus IR minus VL equals 0. So that's my loop rule. Let me just dwell on this for a minute. I have a voltage rise, and then I basically lose some of that voltage here, and I lose some of that voltage here. And then if you wanted to ask, but this would be a great question, how are you losing the voltage? Because you could say, well, here, as far as the resistor is concerned, you're basically losing energy as heat. You basically have heat dissipation. How are you losing voltage to the inductor? Inductors don't generate heat, but what they do is you convert electrical potential energy to magnetic potential energy. So you're not losing energy. It's not dissipating away as heat. It's just being gobbled up in the form of magnetic potential energy. And that magnetic potential energy does, once again, try to fight any changes in current, which is why I'll do this one more time. You could think of this as what the inductor is doing I underscore induced, or inductor, that works as well. So number 3, okay, number 3, we've got to get the EMF of the battery. So here's the EMF of the battery. The EMF of the battery equals IR plus VL equals IR plus L di dt. So this is what we're left with. We're left with my EMF, which is a function of t. I'm just drawing this argument t. I don't always do that, but I'm just doing it here just to underscore the fact that this is a time-dependent voltage source. So this voltage source, which is a function of t, equals IR plus L. So I didn't do anything different here apparently, other than write the argument t, L di dt. And I guess you're good to go, because at 6 seconds, at time equals 6 seconds, what is my battery voltage? What does my battery voltage need to be to produce this current response? So again, this is what the current needs to do. The current needs to follow this graph, needs to be described by this graph. So you're looking at my current profile. And so at 6 seconds, if I have to stay adherent, if I need to adhere to that current profile, then we got our answer. We know what the EMF needs to be doing at 6 seconds. It's going to equal I, and for me, I is 1.5 plus 6t times R plus L d by dt of my I function, 1.5 plus 6t. And you need to evaluate all of this at 6 seconds. Eraser. So step 6 is my EMF at 6 seconds equals all of that. Okay. Quiz 8 ready. $145. Okay, you should now see quiz 8. So if you're ready. All right. After switch S is closed at time equals 0, this switch gets closed. That constitutes time equals 0. The EMF of the source is automatically adjusted to maintain a constant current of I equals 1.22 amperes. So basically, there are two kinds of circuits. There are two kinds of sources. There's a voltage source, which we are very accustomed to dealing with, and there's something known as a current source. And basically, a current source will do whatever it needs to do to maintain a certain input current. And it's done through circuits like we've been working with, through a combination of resistors and capacitors and stuff like that. But for now, we're just going to consider this a black box. For now, when you close the switch here, this constant current source, this is now a closed switch, will produce, in my case, a current of 1.22 amperes, no matter what. So no matter what's going on with that inductor or that resistor, this is going to be 1.22 amperes. Okay. Part A, find the current through the inductor at 34 tau L. All right, so let me just jump into that. All right, find the current through. So for current, inductor current, step number 1, inductor current is described by what I have right there. Inductor current described by I equals EMF over R. And this is very analogous to what we dealt with RC circuits, minus T over tau L. So a few words about this expression, which again, I have copy and pasted up in the right corner. This is what happens when you take an RL circuit and you analyze it using Kirchhoff's loop rule and just some other operational steps. You basically get this logarithmic function. This function right here, if I plot this, if I plot what I highlighted in green, this is what I get, and this is logarithmic growth. So this is logarithmic growth, so that's worth mentioning. Another thing worth mentioning is this inductor time constant right here. This is known as my inductor time constant. We've seen stuff like this before. I mean, multiple times. You remember in thermodynamics, we were seeing the occurrence of CP over CV so many times we gave it a name. We called it gamma. And then when we were studying RC circuits, we saw the occurrence of RC so many times in the differential equation that defined all of this, is we gave that a name as well. And that was tau, maybe tau sub C. This is the capacitive time constant. Capacitor time constant. So it's just the same game we're playing here. We're seeing the occurrence of L over R so many times that we're going to just cough up a shorthand notation called tau, which is the inductor time constant. And just like any time, so this is true for population studies and microbiology, cellular division, or compound growth. Whenever you decide to wait for one time constant to tick off the clock, so you go ahead and you start your stopwatch and you say, I'm going to wait for one time constant. So this is my time axis. So let's all just decide to wait for the passage of this much time, the passage of one time constant. At that point, you've achieved here at time equals tau, you've achieved 63.2% of your outcome, of steady state outcome, ultimate outcome or steady state outcome. And you can see from this graph that if you wait for one time constant, you go from 0 amperes all the way up to 0.632 times the maximum value. This over here, I could write this as I max. So there's a lot of stuff. This is a pretty simple problem, but I'm squeezing a lot of stuff out here because this is the fundamental stuff. So that's the meaning of tau. Tau is L over R. It is, the units are in seconds. So tau is given in terms of seconds. So apparently, if you did the dimensional analysis, you would do L over R is Henry over ohm. So apparently a Henry over ohm equals a second. So that's the dimensional analysis that you have to be comfortable with. Anyway, having said all of that now, and I'm going to make these points kind of again going forward at this point, but that gets us going. Part A is find the current at 34 time constants. So here's the answer. The current at T equals 34 tau subscript L equals EMF over R times 1 minus E to the minus 34 inductor time constants all over inductor time constant, and that's the answer. So you have to ask yourself, number 3, at 34 time constants, 34 times the time constants, I'm going to take EMF over R times I guess you could do this on your calculator. You could do this on your calculator. What is E to the minus 34? And the answer is, according to your calculator, and just looking at it, well, it equals 1 over natural log base E to the 34th, and basically comes very, very close to 0. And if you didn't feel comfortable saying, that's pretty close to 0, just go on your calculator, just do natural log base E to the minus 34, and you're going to get a super duper small number, which kind of makes sense because it's saying if you wait 34 time constants, here's what happens if you wait one time constant. If you wait one time constant, you're at 63.2% of your maximum current. Now imagine now, instead of waiting one time constant, I wait 2, and then 3, and then 4, and then if I go out to 34 time constants, 34 tau subscript L, I'm pretty much flatlining. This is asymptotically approaching this. So if I wait all of that time, which is a long time as far as this circuit is concerned, then basically I've hit. I'm asymptotically very close to my EMF over R, because again, this whole term basically goes to 0. Okay, so that's part A. Pretty anticlimactic. That's why the answer to part A is I've reached my steady state current. So at 34 time constants, I am, for all intents and purposes, at my steady state outcome, which is I max. And Ohm's law. Ohm's law says that V equals IR, so I equals V over R. Anyway, let's do part B, number 4. Part B, what is the time when the current through the resistor is equal to the current through the inductor at tau L equals 5? So we're saying, hey, wait for 5 time constants, 5 seconds. I shouldn't say 5 time constants. Let's wait for 5 seconds. Assume tau L. Sorry, and that's not, I didn't say that quite right. We're basically just saying tau L, tau subscript L equals L over R, and it equals 5. And it's a good thing they gave us that, because did they give us the value for R? Nope. And did they give us a value for L? So I don't know what L is. I don't know what R is, but they said my inductor time constant is just 5. So fine, 5 seconds. All right, so number 4 says this. Well, before I guess we go there, when is the current through the resistor equal to the current through the inductor? So you have to ask yourself, when does this situation arise? When am I going to have the current going through the resistor equaling the current going through the inductor? So that's what we have to figure out. When do I have those two currents equal to each other? And here's my junction. So you can see my circuit current's going to enter that junction. And part of that circuit current, from my current source, part of that current is going to turn right at the junction. And I'm going to just call that I subscript R. Some of it's going to go through the junction, going to go rightward. Some of it's going to, again, go downward. Some of it's going to go rightward. And this I'll call I subscript L. So really part B is saying, when are they equal? Part B is saying, when is the current through the resistor going to be equal to the current through the inductor? That's what we're asking. What is the time? So, okay. I guess this is just a straight up application of my current behavior through an RL circuit. So this is my current behavior. And I guess I'm just going to stick with L. I'm just going to say the current going through my inductor is given by this expression thanks to Kirchhoff's loop rule and some calculus and various knickknacks. You get this logarithmic expression, logarithmic growth, because we are talking about a charging inductor, T over tau L. And we actually have a number on that. We know that it needs to equal I sub R. And maybe I'll sidebar this part. We know that if I sub R equals I sub L, then you could say IR equals 1.22 over 2 equals IL. It's basically saying when they're equal, half of this 1.22 amperes goes through the resistor and the other half goes through the inductor. So that's why I can say that the half of my current source current that goes through the inductor is just going to be 1.22 over 2. So we have a number on that. So I'm not sure how much longer to keep going with this before, because you should be able to see 1.22 amperes over 2. That is the value of IL. So I have a value for IL. That's the 1.22 over 2. And that's going to equal my EMF over R, which do I know the EMF? Yes. I mean, do I? So no. So right now, this is a big oh no, but I'll just keep going. 1 minus e to the minus t over tau L. Okay, so I'm feeling pretty good. Here's my $sign right here. I'm after, what is the time? So this is my $sign. You got to find out the time at which the current going through the inductor is equal to the resistor, which is 1.22 over 2. So I'm okay with that being unknown. I do know the value of my time constant. It's 5. But I don't know E and I don't know R, but that's not a big deal because Ohm's law is saying V equals IR. If V equals IR, then I equals V over R, and V is just my EMF over R. And I know what this is. I know what this is. This is my circuit current. This is 1.22 amperes. So if you go back up to this graph of current versus, this is a graph of current versus time. This is asymptotically approaching my steady state current. And again, for this problem with my numbers, this is gradually, the current going through the inductor is gradually going to grow to 1.22 amperes. Why? Because as time goes by, this is going to start looking like a wire. Will look like a wire because of that inertia. It's that fan blade that starts spinning, will look like a wire after a good long time. So after a good long time, this looks like a wire. All the current's going to ignore the resistor and just go through the inductor. So there, I think I've said enough. Okay. So go ahead and solve for T. What time is it? 2 o'clock. Let's do this. It's 2 o'clock. I need to set up some other, so we have one more quiz and I have to set up something else. So let's do a 10-minute break right now. So keep working on this if you still need some time, but I will see you guys at 2:12 because I need to get some other stuff ready for after the last quiz. So 2:12, we officially restart.
I just have a question about the question.
Yep.
So we were trying to figure out the time where IR is equal to IL. So in that number 6, so is that right side of the equation IR, or is that just?
Yeah, it is actually. I mean, that's a good question. This whole side right here, this side of the equal sign, all of this is the current going through my inductor. So you're right. All of this represents the current going through the inductor, which is a function of T, which is given by this right here.
Okay, so that's the
right.
Inductor, and then the other one, that's the resistor, which is the half. Okay.
Not really. No, I mean, this one on the left side, that's, well, it's yeah, I mean, basically we're saying when is the inductor current equal to half of my source current? And yeah, it so happens it's going to, at that instant in time, and only at this instant in time, the inductor current is going to equal the resistor current. So I think you're thinking about it the right way. I just want to make sure that.
Because that's not always the case. Obviously.
Yeah, exactly right. Exactly right. Okay. So see you guys at 2:12.
Oh, I'm sorry. I actually also have a question.
Yes.
So I got part B right, but I thought part A was just what I is, like what's given to you, but it's saying like that's not right.
Well, I mean, do you tell me, Angela, why is A just the current? Why is, I mean, descriptively, you explain to me why part A is just the value of the current.
I really don't know.
Yeah, so let's circle back and talk about that, because otherwise it sounds like what you're doing is you're just listening to the last 10 seconds of what I said about what the answer to A is and trying that number. So rather than do that, it's going to be a lot better for you if you kind of go back and revisit steps 1 and 2. So give another look at step 1 and 2. Here was step 1. Here was step 2. And then I yammered on, I ranted on about, well, 34 time constants, waiting 34 time constants. That means you're way out here. So here's 34 time constants later, which means you're kind of at the flatline portion of this, and this flatline. So yeah, so I really want to encourage you and everyone, just avoid that. Avoid just listening for the last 7 seconds of my 15-minute rant and then plugging numbers in at that point. So give a good look to step 1 and 2, and maybe you have a Wiley Plus issue. I'm not sure, but let me come back at you in about 10 minutes. So this is all about energy, and just because of habit. Yes, this is a positive. This is a negative. This is a positive. This is a negative. This is a positive, and this is a negative, and This is this EMF here is my inductor voltage, and I'm just gonna just throw in some background bits and pieces. I know that at any point my inductor voltage is fighting the imposed voltage. So this is L di dt, and I know that Ohm's law says that I equals V over R. So anyway, and I know that the current going through an inductor is equal to EMF over R 1 minus natural log base E. So this again, this expression was derived for you in the green sheets. So I'm just sort of thinking out loud here in terms of just setup, like, you know, biding my time. All right, so in general, all of this seems to be good. How much energy is delivered by the battery in the first 5 seconds? So let's start. Number one, how much energy is delivered by the battery in the first 5 seconds? And let me just go to the green sheets, and specifically chapter 27 was where we first encountered expressions for electrical power, I think. Chapter 20 charge fields, circuits. Okay, here. So let me just go to this section called power and circuits. And we had this development that you see on your screen. Now, so these 5 boxes basically got us to, or these 4 boxes got us to the 5th box. And all of those are expressions for power, electrical power. So let me just take a snip out of here, and then we should talk about which one do any of these apply to our situation. I mean, sort of my default position, whenever I think of electrical power, I think of I squared R. So my instinct is to bark up this tree, I squared R, in terms of getting, grabbing hold of an expression for power. But then if you read the question, if I read the question carefully, it says, how much energy is delivered by the battery in the first 5 seconds? So just reading this multiple times, how much energy is delivered by the battery in the first 5 seconds, I can't help but think of power as a starting off point, because power is the rate of energy. Power is the rate of energy production or consumption as a function of time, or alternatively, it's the rate of work that gets performed as a function of time. From a differential point of view, it's dE over dt, but we're dealing with circuits here, so maybe and on. So the conversation like that goes on, it's also equal to F times velocity. So I'm thinking in terms of power only because of this variable right here, E. This E stands for energy. So I am thinking of, well, if power is energy per time, and part A is asking how much energy is delivered over a certain amount of time, 5 seconds, this is why I'm thinking of this expression right here, generically speaking, because if I generically think along those lines, then I could say, well, okay, since power is defined as energy over time, that means energy is just going to be power times time. And then I'm thinking, but it's going to, I'm thinking integral calculus. And I'm thinking integral calculus because, as shown here on this screen, which is now pretty messy, let me just take a snip of here. Current's not constant. So current grows logarithmically. And I'm not sure if that means anything, but but what I am thinking is, as time goes by, so as time ticks off the clock, my current's changing. It's undergoing logarithmic growth. This is a charging capacitor. And then during the first 5 seconds, let's just say for the sake of conversation, here's 5 seconds right here. This is t equals 5 seconds. So I got to figure out what the total amount of energy delivered by the battery during that 5 second interval. And then thinking, this is not quite so simple because I have variable, my current's variable. So if I go back to this, I'm going to zero in on this, because this is power dissipated by resistor. Power dissipated by resistor. And that's not what the question is asking, although maybe it does. Maybe part C asks that. Part C is asking for the power dissipated by the resistor. So that's good for part C, but not good for part A. So for part A, this in this case, this would be power delivered by battery. Power delivered by battery. And kind of, I guess it's a little bit process of elimination. This is I squared R. So this is power dissipated by a resistor. You could also say this is power dissipated by resistor. So I kind of hate to say, well, it's process of elimination, but I'm left with P equals IV for the power generated by the battery. So let's just keep going here. Now, this equals I, which is well, you know what I better do now? I better differentialize. It's time to differentialize. And why did I stop myself and say, oh, I better differentialize? It's because I need to deal with a function, not just constant values. So let's see. If I differentialize, dE equals P dt. Okay. So that's my differential expression for the amount of energy fed by my battery. And I like that as my official starting point, because now to get the total amount of energy, I just integrate. And I need to integrate because I need to add up every little infinitesimal contribution at every infinitesimally small time step from 0 to 5 seconds and add them all up. And that's what I do with this integration. So number 2 is, okay, so the total energy delivered in 5 seconds is the integral of dE is the integral of power, which is IV. That's IV times dt. And I'm going to update this. This specifically is going to equal current going through the resistor. So this will be EMF over R 1 minus E to the minus T over tau L. That's what this is. To Ryan's point again, this is describing, this is inductor current. Inductor current. And you might ask, like, why am all of a sudden, if I'm wondering about the energy delivered by the battery, why do I all of a sudden turn my attention to the current going through the inductor? And the answer is because that's the limiting factor. Because the current that goes through the battery or through the resistor is going to be limited by the inductor, because this inductor has that stubborn personality that always wants to resist change. So again, collectively, this is my current I, and whatever the current is going through the battery is the same as the resistor, it's the same as the inductor. So this is I, and here's V. Voltage is my EMF. So that's IV. So collectively, again, I have, here's my IV. And now all I have to do is multiply that by dt, my variable of integration. And then the rest is calculus. All right, so I just want to be because now we're just in calculus world, so I'm confident now. But just a few notes. This is my steady state current, because remember, if you wait long enough, this inductor is not going to put up any resistance. It's just going to be accommodating the full maximum asymptotically reached current value. All right, so I guess that's good. So then all we have to do is integrate from 0 to 5 seconds. And I guess we're done. Well, let's see, number three. So the energy after 5 seconds is going to equal, or any constants there yet, EMF squared all over R, integral from 0 seconds to 5 seconds of 1 minus e to the minus t over tau L dt. Okay, I'll go a few more steps up and then leave you to it. Oh, but there's part B too, and C. E equals E squared, EMF squared over R. I guess I'll do it like this. Well, not yet. Times the integral of dt minus integral of dt minus the integral of e to the minus t over tau L from 0 to 5. All right. So let's get that value. The battery delivers this much energy in 5 seconds. E squared over R times T minus E to the minus T over tau L all over minus T to the over tau L. There. Evaluated from 0 seconds to 5 seconds. All right, so let's get an answer on A and then we'll do B and C. So go ahead and finish that off. I'll do the same thing. Except little typo. Let me fix my typo. Let me fix this. This should be 1 over tau L. I'm just going to put tau in my I'm going to sicken my tau, store in calculator memory. L over R. Okay. status check. Chapter 30 quiz. Okay, I think it's time to move on. And some people are completely done. For those of you who are completely done with chapter 30 quiz 9, I'm not saying you did this, but I'm guessing you reached out to Chegg or Slater, which is cool. I'm just saying, go ahead and do that. But in addition to do that, actually do stay connected to our conversation so you actually learn the deep roots of these solutions. It's a difference maker, especially if you're interested in improving your exam scores. You should take a really sort of skeptical look at Chegg or Course Hero or Slater or whatever site you're accessing right now to look up the answers. So just a little nudge to fight the good fight, because I noticed a couple of you got this complete question answered correctly in a remarkably short amount of time. So just beware. Having said that, let's go to part B. Part B is now saying, and the interesting, those of you who answered part B did so without any comments about what part B is. How much energy is stored in the magnetic field of the inductor? So even if you slated this answer, this hopefully will still be beneficial to you. Slater will get you credit for the quiz, which is kind of not really too meaningful when you compare it to the exam. So part B says, how much of this energy is stored in the inductor? And this is a job for green sheets, which let me share that. And there's some useful comments we can have about magnetic field energy. We've talked about electric potential energy. Now we're talking about magnetic potential energy. We like inductors because they store magnetic fields, which is anything that can store energy is we are just instantly interested in. So there it is. I'm on the screen. I'm where I need to be. And I guess this is good. So these boxes right here, energy in a magnetic field, it's pretty short and sweet. Energy in a magnetic field is derived, again, thanks to Kirchhoff's loop rule and some differential calculus. It's pretty rudimentary, not real heavy lifting. But at the end of the day, we see something that looks really familiar. We see steps E and F right here. And F is saying, look how similar this is to stored electric energy, stored electric field potential energy in a capacitor. Capacitors store electrical energy, inductors store magnetic potential energy. So that's why we like them. And this is the expression derived, pretty straightforward derivation, but live through the derivations and we're going to be done. We're basically done because part B is basically saying, what is the magnetic field? How much of this energy is stored in the magnetic field of the inductor? And the answer is 1/2 L I squared equals 1/2 L, which is given 6.2 henries for me. And I is what we have. I was given by E over R times 1 minus natural log base E to the minus T over tau L. And all you need to do is square that. That's 1/2 Li squared. So pretty straightforward, but again, gives me a chance to give a little bit of the backstory. And there's more good backstory. So again, I'm still cringing. Those of you who somehow, as if by some miracle, finished this question before, as of right now, you're making me nervous, man. You're making me nervous. So I'm just going to try to make it worth your while to listen anyway. 1/2 Li squared. All right.
Still showing the green sheet screen.
Oh, okay. There. So again, super simple, super operational approach, but that was my commentary to make you a deeper thinker, a better problem solver. And then I'll go on and add some notes for part C. Part C. All right. Well, at t equals 5 seconds. At t equals 5 seconds, my battery delivered in my case 116 joules of energy. At this time. So I'll number this. I'll call that 1, 2, 3. Where's the missing energy? So for part C, assume you guys are all done with part A and B. At 5 seconds, my battery has delivered this much energy. 100 joules of energy. At 5 seconds, at the 5 second mark, my inductor only has this much energy. So just looking at my answers here, after 5 seconds, my battery has produced that much energy, 116 joules. At 5 seconds, though, of that 116 joules, only 12 joules is residing in the magnetic field of my inductor. So the question is, where's the remaining energy? And the answer, where's all the other energy? Where's all the other energy provided by the battery? So you just subtract one from the other. Where's all the other energy provided by the battery? And the answer is it got burned up. It got burned up in the resistor. So answer, the resistor dissipated it as heat. The resistor dissipated it as heat. So I'm giving kind of like a mini essay response to part C, which, because to me, this is like the bigger picture thinking. The resistor dissipated the remaining energy in the form of heat. And the remaining energy is given as this. It's just going to be my 116.6 joules of energy provided by the battery minus the 12.66 joules that's living in the inductor. And that is the energy. That is my I squared R. That is the energy dissipated by the resistor. So I squared R equals energy dissipated by the resistor. And if you wanted to, you could forget all of this mini essay description and say, well, you know what, Chris, that's all nice and well. Always fun to read essays, but instead, you know what I'm going to do? I'm just going to do I squared R. I squared R is the power dissipated by the resistor, and then go through sort of a similar series of steps where energy is going to be integral of P dt. So, but this is the shorter way. Step 4 is the step 4 approach is going to be easier than the step 5. Plus, I think it's more insightful. This is a good problem because it focuses on energy, not just current values or voltage values. It's energy. And in so many ways, energy is the ultimate thing that we care about.